When you gaze into the night sky, you're staring into a terrifyingly silent void, but the truth is, the universe is actually screaming at us. Beyond the soundless gulfs between galaxies lies a hidden symphony of ancient light and violent energy, revealing that the cosmos isn't truly quiet. It's just speaking a language we're finally learning to hear. I'm genuinely curious about your exact physical location as you watch or listen to this presentation tonight. Perhaps you are resting in a peaceful, shadowy bedroom with the soft illumination turned down low. Maybe you are traveling on a midnight transit route connecting two distant towns, quietly watching the dark world blur past the window. Alternatively, you could be lounging on a plush couch with a comforting, hot beverage resting right beside you. No matter your specific geographic coordinates on the globe, the ultimate goal is for you to feel completely at ease, deeply relaxed, and fully prepared to smoothly transition into our evening's fascinating subject matter. Take a deep, calming breath, let your tired shoulders drop, and allow your curious mind to gently wander into the new concepts we are about to explore together tonight. As your thoughts begin to drift, our subject for this evening might strike you as slightly unexpected. When we truly examine the cosmos, it turns out to be far less noisy and disorderly than popular belief often suggests. Actually, calculating the massive gaps separating distant galaxies and stars reveals a fascinating reality to modern researchers. Space is profoundly silent. This deep silence does not mean the cosmos is entirely inactive. Quite the opposite is true, with giant suns detonating, massive galaxies crashing into one another, and giant black holes consuming whole solar systems. Yet, the sheer, massive void of empty space dilutes these spectacular occurrences, turning them into a remarkably serene backdrop. Looking up from our minuscule home on Earth, the heavens seem remarkably tranquil, motionless, and hushed, almost as though existence itself heavily favors tranquility. This naturally brings up a fascinating puzzle. What exactly makes the cosmos so exceptionally silent? Gazing upward on a cloudless evening, the atmosphere feels overwhelmingly serene, with stars suspended peacefully above us like faraway lamps dotting the dark. Rather than racing, flashing erratically, or bellowing, these celestial bodies remain remarkably composed, remote, and enduring, with even the most luminous ones offering nothing more than a gentle shine. Throughout the vast majority of our past, this tranquil perspective was humanity's only frame of reference, ultimately inspiring vastly distinct theories regarding the true nature of reality. Building on those early theories, ancient stargazers never pictured the night sky as a vacant void. Instead, they envisioned a highly organized framework, functioning much like a multi-tiered mechanism. The Greek thinker Aristotle suggested the universe consisted of flawless heavenly orbs. These spheres supposedly transported stars and planets in smooth, circular paths around our planet. Under this paradigm, existence was highly structured, elegantly balanced, and completely filled, despite its peaceful appearance. Later, Middle Ages intellectuals adopted and expanded these concepts. They pictured the sky as concentric shells crafted from an enigmatic, perfect material called quintessence. Within this model, our moon occupied its own layer, the sun traveled in a separate one, and faraway stars were glued to an ultimate outer boundary gently spinning around creation. This cosmic design felt incredibly whole and architectural, yet remarkably compact. Even the most visionary philosophers of that era conceived of a universe barely bigger than our solar neighborhood. While they knew stars were far away, the distances were nowhere near the mind-boggling proportions we recognize today. Ultimately, they lacked any concept of the immense, breathtaking scale that contemporary science would later uncover. This massive shift in understanding didn't happen overnight. When the telescope arrived in the early 18th century, it gave researchers tools to observe the cosmos with incredible clarity. The night sky transformed from a simple backdrop of scattered dots into a complex canvas filled with glowing clusters, hazy clouds, and mysterious smudges floating between stars. Initially, the true nature of these strange sights remained a mystery. While some experts guessed they were local gas pockets, others suggested they were faraway star systems. This lingering confusion stretched on for decades, silently setting the stage for a monumental astronomical clash. That epic showdown finally unfolded in the early 20th century, spotlighting two brilliant stargazers, Harlow Shapley and Heber Curtis. Famous today as the Great Debate of 1920, their historic argument boiled down to one seemingly straightforward puzzle. What are the true dimensions of the cosmos? Shapley championed the idea of a gigantic Milky Way, insisting that the weird spiral nebulae spotted by telescopes were merely tiny gas pockets floating inside our own galactic home. Curtis, on the other hand, proposed a much wilder concept, arguing that these swirling formations were actually completely separate galaxies, massive star clusters sitting way past the edges of the Milky Way. Back then, both of these possibilities sounded completely reasonable to the scientific community, meaning this legendary dispute was not actually resolved right on the spot. However, that scientific stalemate wouldn't last for long, because a massive, silent breakthrough was actually just around the corner. At California's Mount Wilson Observatory, an astronomer named Edwin Hubble began studying the night skies using the 100-inch Hooker telescope, which was the most powerful instrument on Earth at the time. Pointing this massive device at a faint, blurry spiral known as the Andromeda Nebula, Hubble managed to pick out individual stars hidden inside the hazy formation. He noticed their light pulsed in a very steady, predictable rhythm. These are known as Cepheid variables, whose secrets had been previously unlocked by the brilliant researcher Henrietta Swan Leavitt. Leavitt discovered a remarkable relationship. The time a Cepheid takes to complete its brightening and dimming cycle is directly tied to its true luminosity. Measure that pulse, and you know exactly how much light the star actually emits. By comparing that intrinsic brightness to how dim the star appears from Earth, astronomers could easily calculate its exact distance. When Hubble ran these calculations for the Andromeda stars, the final result was absolutely astonishing. This fuzzy object sat far beyond the boundaries of our own Milky Way. It wasn't a local nebula at all. It was a completely independent, separate galaxy. Instantly, the universe expanded from a solitary galaxy into a vast, sprawling collection of them. Each of these galaxies contained billions of stars, floating through unbelievably immense stretches of empty space. Almost overnight, the sheer scale of the cosmos had become mind-bogglingly vast. Alongside this mind-blowing expansion in size came a striking new truth. The cosmos is overwhelmingly empty, and we aren't just talking about a little bit of empty space. The gaps separating different galaxies stretch for millions of light years. Even when you look inside a single galaxy, the stars are divided by massive, unimaginable voids. Take our own solar system, for instance. The closest star system to us, Alpha Centauri, sits roughly 4 light-years away. To put that in perspective, light, the absolute fastest thing in the natural world, needs over 4 full years just to bridge that single gap. And what fills the space between our sun and its neighbor? Practically nothing. You only find a sparse dusting of atoms floating through the interstellar medium. This massive void completely changed how scientists viewed the night sky. They realized the cosmos wasn't a crowded, clockwork machine filled with touching celestial spheres. Instead, it was a bizarre, sprawling framework built almost entirely out of nothingness. Cosmologist Edward Harrison thought deeply about this concept while examining the universe's large-scale architecture. He noted that the cosmos seems quiet not because it lacks activity, but simply because of how space is geometrically arranged. Gravity pulls matter together into tight clusters and galaxies, leaving the remaining space to stretch out over unfathomable distances. Because of this layout, the universe looks incredibly peaceful from a distance. However, that peaceful appearance is a total illusion. Deep inside galaxies, dense gas clouds are constantly birthing new stars. In other regions, giant stars detonate as supernovae, releasing enough energy to temporarily outshine their entire host galaxies. You have black holes devouring material, neutron stars smashing into each other, and intense radiation beams shooting through the voids between galaxies. Still, because the universe is so unbelievably huge, these violent occurrences are spaced so far apart that the overall vibe remains tranquil. This paradox absolutely captivated theoretical physicist John Archibald Wheeler. Throughout his career, Wheeler explored the fundamental fabric of reality, diving into everything from quantum mechanics to black holes. He frequently pondered a seemingly basic mystery. Why does a cosmos bursting with such extreme energy look so incredibly serene from a distance? What makes the night sky feel so relaxing instead of wildly chaotic? A huge part of the explanation is simply the sheer size of it all. When cosmic events happen millions or billions of light years apart, they almost never overlap in our field of view. Rather than a raging, non-stop storm, we just see tiny, isolated twinkles in the dark. Yet the other half of the explanation comes down to the actual physical properties of space. The universe's tranquility isn't just about things being far away, it is also about literal silence. The massive voids separating galaxies and stars do something pretty amazing. They block almost all vibrations from moving through the cosmos. When a distant star blows up, it doesn't boom and crash like thunder echoing through the sky on Earth. Those massive explosions happen in almost total, perfect silence. This brings up a really fascinating perspective. The cosmos might not be quiet because it's boring or inactive. It might just be missing the physical ingredients required for us to actually hear the action. To really grasp this concept, we first need to ask a very basic question: what actually is sound? To answer that and understand cosmic silence, let's start with our everyday reality. Here on Earth, noise surrounds us constantly. Whether it is leaves rustling, distant traffic humming, or raindrops lightly hitting a window, even tranquil spots buzz with activity. Invisible, microscopic tremors continuously travel through the air around us. However, audio isn't just a standalone entity. Instead, it functions as an active mechanism. Fundamentally, we are dealing with mechanical tremors journeying through physical substances. Whenever an item shifts or collides with something else, it forces adjacent microscopic bits to bounce around. This kinetic energy transfers sequentially from one bit to the next, expanding outward exactly like rings radiating across a pond. Our ears simply interpret these moving waves as audio. Our atmosphere is a fantastic conductor for this energy. When speaking, your vocal folds rapidly shove air molecules back and forth. These bursts travel outward until they hit a listener's eardrums, translating physical pulses into neural signals. Liquids are also excellent transmission mediums. Actually, audio travels much quicker through water than air, allowing whales to communicate across massive underwater stretches. Dense solids work perfectly, too. By pressing your ear against a steel railway track, you can detect an incoming train long before hearing it through open air. Every scenario shares a crucial ingredient: physical matter. Audio demands tiny building blocks. It relies on atoms and molecules packed tightly enough to crash into each other, relaying energy in a sequential chain. Without those bits, the tremors have nothing to propel them forward. While this seems obvious today, early researchers weren't entirely sure how audio acted in a total void. In the 17th century, scientists began testing methods to create artificial vacuums by removing air from sealed containers. A major pioneer was the German scientist Otto von Guericke. He famously demonstrated this using two large metal hemispheres joined together and evacuated of air. Teams of horses straining to pull the halves apart failed, revealing the immense power of atmospheric pressure. Yet, von Guericke also explored a quieter mystery: what happens to audio when air is removed? His experiments suggested that sound weakened dramatically in a vacuum. Later scientists refined these tests, notably the English physicist Robert Boyle. He placed a ringing bell inside a glass chamber and gradually pumped out the air. As the air disappeared, the bell kept vibrating, but its sound faded until it was nearly impossible to hear. The bell was still ringing, but the sound had nowhere to go. These early vacuum experiments established a key principle of acoustics: sound requires a medium to travel. Remove the medium, and the vibrations remain trapped at their source. Later, scientists expanded this understanding by studying how vibrations move through different materials. In the 18th century, German physicist Ernst Chladni conducted elegant experiments with vibrating plates. By sprinkling fine sand across metal plates and drawing a violin bow along the edges, Chladni made them vibrate in specific patterns. The sand gathered into intricate geometric shapes, revealing how sound waves moved across the surface. These patterns, now known as Chladni figures, provided some of the earliest visual demonstrations of wave behavior in solids. A century later, Hermann von Helmholtz deepened our understanding of acoustics by studying how sound waves interact with physical objects and the human ear. He showed that sound could be analyzed mathematically as oscillating pressure waves moving through matter. Put simply, sound is motion passed from particle to particle, which brings us to space. When we look out into the cosmos, we immediately run into a massive problem for that particle-to-particle motion: the sheer emptiness of the void. The cosmic gap separating individual stars is barren to a degree that defies human imagination. Down here on our planet, a tiny pocket of the purest atmosphere still packs billions of microscopic molecules. Out in the deep cosmos, however, you might find just a handful of atoms in a single cubic centimeter, or occasionally even less. Scientists refer to this incredibly sparse mist as the interstellar medium, a concept heavily researched by the 20th century astrophysicist Lyman Spitzer. His work demonstrated that while the universe looks totally barren, it actually harbors delicate wisps of hydrogen, tiny specks of dust, and roaming ionized bits. Yet the crucial detail is just how delicate those wisps truly are, because these specks are spaced so far apart, they almost never bump into each other. Picture yourself inside a gigantic room where the next human being is standing several kilometers away. Trying to pass a physical shove down a line of people in that scenario would be completely futile. This perfectly illustrates the reality of the interstellar void. Consequently, when a massive star detonates in a brilliant supernova, it blasts incredibly fast shockwaves into its surroundings, but those ripples rapidly dissipate as they expand into the extreme vacuum. The scattered atoms are just too distant to carry a steady acoustic ripple over any meaningful stretch. So, while the blast unleashes a mind-boggling amount of power, the entire catastrophic event plays out in total quiet. Of course, this lack of noise doesn't imply the cosmos is completely stagnant. Actually, the void is buzzing with alternative energy types that navigate the dark using entirely different mechanics. Take light, for instance. It effortlessly glides through the vacuum since electromagnetic waves don't need physical matter to propagate. Instead, they ripple right through the very structure of the universe, ferrying data and power across unfathomable gulfs. You will also find some highly unusual types of movement out there. Whenever cosmic gas gets ionized, meaning its atoms get stripped of electrons, the resulting bits carry an electrical charge. These charged specks react intensely to magnetic forces, generating intricate movement patterns that we call plasma waves. The brilliant Swedish physicist Hans Olfvén dug deeply into these occurrences, ultimately founding the discipline of magnetohydrodynamics. This specific area of science examines the relationship between magnetic fields and electrically conductive liquids, like plasma. Olfvén proved that within particular cosmic settings, ripples can surf along magnetic field lines through ionized gas, shifting energy in a manner that mimics acoustics yet is entirely driven by electromagnetism. While these plasma ripples are incredibly cool, you shouldn't confuse them with regular audio. They only happen under highly specialized circumstances and definitely don't sweep through most of the interstellar expanse. When it comes to standard noise, the rule is straightforward. Atoms need to be packed tightly enough to bump into their neighbors. Out in the deep cosmos, that simply isn't the case. That exact principle explains why spacewalkers hovering outside their ship would be completely deaf to a nearby blast, unless the shock physically rattled the hull they are touching. The empty void around them offers absolutely zero bridge for acoustic waves to cross. Therefore, the cosmos remains deeply hushed, not from a lack of dramatic action, but because the sheer emptiness between those actions blocks acoustic travel. Still, this acoustic dead zone only tells half the tale. Far more mind-blowing than the sheer emptiness is the colossal gap stretching from one star to the next. These gaps are so unbelievably huge that whole planetary systems wander the galaxy without ever getting anywhere near their neighbors. Once you truly grasp that monumental scale, the hushed nature of the cosmos stops being a mere curiosity. Instead, it just feels completely unavoidable. Moving past that unavoidable quietness, we immediately confront another defining trait of the cosmos: sheer distance. We aren't talking about the familiar stretches we know on Earth, where a road trip between cities covers a few hundred kilometers, or where vast oceans span a few thousand. The gaps separating stars operate on a completely mind-boggling level. These spans are so incredibly massive that our human brains simply cannot visualize them properly. Take Alpha Centauri, for instance, which holds the title of our closest neighboring star system. It sits just over 4 light-years from us. To put that in perspective, light, the absolute speed champion of the natural world, needs over 4 full years to make the journey from there to Earth. 4 whole years, and that is our absolute closest neighbor. Even though the Milky Way houses hundreds of billions of stars, gigantic voids of nothingness divide them. Think of our solar system as a minuscule gravitational sphere dominated by the Sun. This sphere extends for trillions of kilometers before the Sun's pull finally weakens. Past that invisible edge, you enter a pitch-black interstellar void that demands years of light-speed travel just to reach the next stellar neighbor. Imagine shrinking our Sun down to the size of a tiny coin sitting on your desk. Even at that scale, the closest star would still be located thousands of kilometers away. Calling the galaxy mostly empty space is actually a massive understatement. Historically, scientists lacked the tools to calculate these mind-bending gaps. Because stars appeared as mere pinpricks of light without any visual depth, figuring out their true remoteness seemed like an impossible puzzle. That all changed in the early 1800s thanks to the meticulous efforts of Friedrich Bessel, a brilliant astronomer from Germany. He applied a method called stellar parallax, taking advantage of our planet's yearly journey around the Sun. As the Earth moves along its orbital path throughout the year, closer stars seem to wiggle just a tiny bit when compared to the fixed backdrop of faraway stars. This apparent movement is incredibly minuscule. Spotting it demanded many years of dedicated stargazing paired with highly accurate equipment. Finally, in 1838, Bessel managed to record the parallax for a star called 61 Cygni. By measuring that microscopic positional change, he successfully computed exactly how far it was from our world. Humanity finally possessed a trustworthy way to gauge the distance to another star. His findings proved exactly what many scientists had already guessed. These celestial bodies are separated by incomprehensible distances. Moving through the 1800s and into the early 1900s, researchers started documenting these celestial objects with much finer precision. Global observatories carefully charted their colors, luminosity, and unique spectral fingerprints. This massive data collection gradually proved that stars weren't just randomly tossed into the void. They formed a massive, structured community spanning the Milky Way. A major driving force behind this progress was Annie Jump Cannon, working out of the Harvard College Observatory. She created a brilliant organizational framework that grouped stars based on their spectral traits, which essentially meant sorting them by how hot they were. We actually still rely on her exact system today. It beautifully illustrated that stars fall into specific families, spanning from blazing hot blue giants down to much cooler red dwarfs. This sorting method gave scientists crucial insights into stellar diversity and galactic distribution. Then came another monumental leap forward from Cecilia Payne-Gaposchkin. During the 1920s, she closely examined starlight spectra and uncovered something truly astonishing. She proved that helium and hydrogen make up the vast majority of a star's mass, completely shattering the old belief that they were made of the same rocky stuff as Earth. Her breakthrough showed that all stars share the exact same basic chemical recipe. This pointed to the idea that our entire galaxy originally coalesced from gigantic gas clouds, which later clumped together to birth individual solar systems. Once born, these individual systems mostly followed their own independent evolutionary paths. The renowned astrophysicist Subrahmanyan Chandrasekhar later dove deep into this concept by investigating the physical rules that dictate how stars are built. He demonstrated that a star's structure relies on a delicate tug-of-war. Gravity constantly yanks everything inward, while the outward push of nuclear fusion pressure holds it all up. This perfect equilibrium is what lets stars survive for astonishingly long stretches of time. Countless stars exist for billions of years without ever drastically altering their movement or luminosity. They just simmer away peacefully, steadily fusing hydrogen into helium deep inside their centers. Basically, after their initial formation, stars relax into incredibly long, uneventful lifespans. This remarkable consistency is a huge reason why the galaxy looks so incredibly serene. Despite packing unbelievable amounts of power, stars drip-feed that energy into space over millions or even billions of years. Sure, you have the occasional rule breaker. A few stars will ultimately detonate as spectacular supernovas, unleashing mind-blowing shockwaves of energy. However, when you zoom out to look at the whole galaxy, these violent blasts are actually quite uncommon. The overwhelming majority just emit a steady, quiet glow into the dark. We also gained a much better grasp of stellar spacing by meticulously mapping how stars are sprinkled across the night sky. One notable contributor to this mapping effort was Radha Gobindachandra, an astronomer from India. Even while relying on fairly basic instruments, he dedicated years to monitoring variable stars and recording how their brightness fluctuated. His relentless tracking, combined with the hard work of countless other stargazers globally, allowed scientists to paint a much sharper image of the Milky Way's population. This collective research gave birth to the idea of stellar neighborhoods. It turns out stars aren't just sprinkled uniformly like salt on a table. They frequently gather into loosely associated clusters or groups that were born from the same cosmic nursery. You can find some of these clusters packing hundreds or even thousands of stars, all kept in a gravitational embrace. However, even inside these crowded families, the physical gaps between neighboring stars are still mind-bogglingly huge. While gravity keeps the cluster intact, the individual suns almost never get close enough to actually bump into each other. As a matter of fact, two stars physically crashing into one another is an almost impossibly rare occurrence. Just look at our very own sun to see this in action. While making its grand lap around the Milky Way's core, it cruises through the cosmos at a brisk pace of about 200 kilometers per second. Throughout millions of years, it wanders through various galactic zones and sometimes passes relatively close to other suns. Still, the sheer scale of these gaps means these close calls basically never result in a crash. Stars just smoothly sail past each other, much like solitary ships navigating a gigantic, mostly vacant ocean. This incredible spacing drastically alters how the universe actually looks to our eyes. Since the gaps are so massive, the light from each star arrives on its own, rather than merging into one giant, blinding sheet of light. Every single star stands out as an isolated speck of brilliance, completely swallowed by massive oceans of blackness. If these suns were huddled much closer together, our night sky would be unrecognizable. The dark voids would vanish, and the sky above might just look like a solid ceiling of unbroken light. But in reality, our galaxy looks more like a widely scattered archipelago of islands floating in a boundless, empty sea. Furthermore, this extreme isolation plays a massive role in keeping the cosmos so incredibly quiet. Whatever chaotic drama happens in one solar system almost never spills over to bother the next one. A massive supernova detonating in some faraway galactic suburb might blast out an unfathomable amount of raw power. However, by the time that radiation manages to cross the colossal void to reach another star, it has faded into a weak, scattered whisper. The universe is undeniably buzzing with activity, but that activity happens so far away that the sheer distance dilutes it all. Ultimately, this leaves us with a galaxy that appears perfectly calm and peaceful, even while enormous, mind-blowing physical processes are constantly unfolding within it. Building on that serene illusion, we have to zoom out and realize our Milky Way is far from unique in this regard. When researchers take a broader look at the universe, an even more astonishing truth emerges. Not only are individual stars separated by mind-boggling gaps, but entire galaxies are isolated by colossal voids of nothingness. Once you grasp the sheer scale of the gaps between stars, it dawns on you that the galaxies themselves are overwhelmingly hollow. Gazing up from Earth, our home galaxy paints a delicate, glowing river across the nighttime canopy. If you venture far away from urban light pollution into pitch-black skies, this celestial band transforms into a hazy, glowing cloud arching right over your head. Historically, people named it the Milky Way simply because of that gentle, milky luminescence. However, this delicate shimmer conceals a colossal architectural marvel. Functioning as a spiral galaxy, it operates as a gigantic, spinning assembly of dust, gas, stars, and dark matter, all locked in a gravitational embrace. The glowing part we can see spans an astonishing 100,000 light-years across, shaping a massive, flat disk that gracefully twirls through the cosmos. Packed inside this disk are hundreds of billions of individual stars. While that figure might sound incredibly crowded, the actual reality is completely reversed. These suns are spread out over such mind-bending distances that even the most densely packed galactic neighborhoods are dominated by sheer vacuum. The typical star floats through a void where its closest companion is several light-years distant. So, while the galaxy is undeniably huge, the void within it is vastly larger. Astronomers have spent decades mapping the shared anatomy of spiral galaxies like ours. Right in the middle sits the galactic bulge, a tightly packed central hub where stars swarm closely around a supermassive black hole. Wrapping around this core is the galactic disk, the expansive, spinning flat layer housing the majority of the stellar population. Cutting through this disk are the iconic spiral arms. Rather than being solid, physical objects like fan blades, these arms are actually traffic jams of density. As gas and stars orbit the center, they bunch up in these zones, creating density waves that squeeze gas clouds and spark the creation of brand new stars. This dynamic process paints the glowing, swirling patterns that make these galaxies look like giant cosmic whirlpools. Moving past the main disk, we find the galactic halo. This massive spherical region reaches high above and deep below the flat galactic plane, hosting rogue stars, ancient globular clusters, and a completely invisible type of material. We call this elusive substance dark matter. The reality of dark matter truly came to light in the 1970s thanks to the brilliant American astronomer Vera Rubin. She meticulously tracked stellar movements in spiral galaxies by analyzing their rotation curves, graphs showing how orbital speeds shift depending on the distance from the center. Standard gravitational rules dictate that stars located further out should travel much slower, since the visible mass shouldn't generate enough gravitational pull to keep them zipping along. Yet, Rubin uncovered a massive surprise. The stars hanging out at the very fringes were zooming around just as rapidly as the ones near the middle. This mind-bending discovery meant galaxies had to possess way more mass than just the visible gas and stars. An invisible, lightless substance had to be pulling on them gravitationally, and thus, the concept of dark matter was cemented. Rubin's groundbreaking work completely flipped our understanding of galactic anatomy. We now know that the bulk of a galaxy's weight is locked up in a gigantic dark matter halo that stretches way past the visible starry disk. Interestingly, the notion of hidden galactic mass was actually floated decades prior by Swiss astronomer Fritz Zwicky. Back in the 1930s, Zwicky was observing galaxy clusters and realized the member galaxies were zipping around way too fast to be contained by just the visible stuff. He deduced that unseen matter had to be supplying the extra gravitational glue, famously dubbing it dark matter. Though largely ignored back then, his early theories were ultimately vindicated by Rubin's later rotation curve data. Nowadays, dark matter is recognized as a foundational pillar of the cosmos. It sculpts how galaxies form, dictates their movements, and ensures these massive structures don't fly apart over billions of years. Yet, even with all this hidden mass, galaxies aren't crowded at all. The physical stars take up a practically microscopic fraction of the total galactic volume. To figure out how these stars are arranged and move, researchers rely on tools like the Faber-Jackson relation, co-developed by American astronomer Sandra Faber. This clever principle connects a galaxy's luminosity to the speed of its internal stars, allowing scientists to calculate internal mass and structure. It beautifully illustrates how gravity orchestrates these massive stellar crowds, always leading back to the same truth: galaxies are incredibly sparse. The bulk of their space is just wandering gas and tiny dust specks, while the stars themselves act like remote islands sailing through a cosmic sea. Looking at how galaxies are born explains why they remain so empty. Current cosmological models tell us they didn't just pop into existence fully formed. They evolved slowly via hierarchical merging. Tiny matter clumps formed in the early cosmos and gradually smashed together under gravity to build bigger structures. Cosmologists like Simon White and Carlos Frenk built intricate computer models to simulate this billion-year journey. Their digital universes proved that dark matter acts as the ultimate scaffolding, creating the gravitational traps where gas can pool and ignite into stars. As these mergers build up the galaxy, the stars get flung across staggering expanses. You end up with a colossal but incredibly fluffy structure. Even with hundreds of billions of stars, the sheer volume means direct crashes are almost non-existent. A whole solar system can complete billions of orbits without ever bumping into another. This extreme spacing is exactly why galaxies look so tranquil from a distance. Sure, intense drama happens inside them. Giant stars implode into neutron stars, supernovas detonate with unfathomable power, and black holes gorge on matter while firing off intense radiation jets. But because these spectacles are separated by tens of thousands of light years, they just look like tiny, isolated sparks rather than a chaotic, universe-wide hurricane. The overall vibe of the galaxy remains totally serene, a tranquil archipelago of stars floating in an ocean of black. And remember, our Milky Way is just a single drop in the bucket. The observable universe holds hundreds of billions of these galaxies, all divided by unfathomable gulfs of emptiness. When scientists chart these galactic positions, they find they aren't just scattered randomly. They clump into massive clusters and long filaments, bordering gigantic voids completely devoid of matter. This grand, universe-spanning architecture is what we beautifully call the cosmic web. Grasping the true nature of this universal network uncovers a profound level of cosmic vacancy. When stargazers initially charted galaxy positions, they anticipated a straightforward layout. Maybe these stellar islands would be sprinkled haphazardly, like sand grains tossed on a beach, or disperse evenly to create a soft haze of drifting stars. However, reality turned out to be vastly more fascinating. Once the late 20th century brought bigger sky surveys, researchers realized galactic distribution was anything but uniform. Rather than spreading out, these celestial cities bunched into massive clusters, long chains, and gigantic sweeping arcs spanning the cosmos. Separating these formations are colossal zones of practically pure nothingness. We now refer to this blueprint as the cosmic web, a visual that stays with you forever. Picture yourself floating far outside the Milky Way, gazing back at the grand expanse. Rather than observing a uniform mist, your eyes would trace a colossal, three-dimensional grid. Elongated threads of galaxies reach through the void, linking tightly packed clusters like luminous strings of silk. These glowing threads interlock to form a complex, universe-wide lattice. Nestled between these starry strands are the barren zones we call cosmic voids. The overall shape resembles a kitchen sponge, or perhaps the fragile froth of bubbles on a pond, only these bubbles span hundreds of millions of light years in diameter. Interestingly, this layout was not a total shock to every scientist. Long before we possessed the technology to chart galaxies across such mind-boggling distances, Soviet physicist Yakov Zeldovich theorized the cosmos might arrange itself into thread-like formations. Zeldovich analyzed how gravity shapes the evolution of matter within our expanding universe, specifically investigating the outcome of minuscule density differences expanding due to gravitational pull. Even during the cosmos's infancy, material was never perfectly mixed. Certain pockets held slightly more mass, generating a stronger gravitational tug that slowly reeled in adjacent material. Scientists refer to this mechanism as gravitational instability. As millions, and eventually billions of years ticked by, those minor density bumps steadily magnified. Zeldovich theorized that when gravity forced this material to collapse, it would not form neat, round spheres. Rather, the matter would initially flatten into broad sheets, subsequently roll into long filaments, and ultimately crunch into ultra-dense intersections where those filaments crossed. Those busy intersections would birth massive galaxy clusters. For a long time, however, this concept stayed purely on paper. Actually witnessing the macrostructure of the cosmos meant charting galaxies over unfathomable distances, a feat older telescopes simply were not equipped to handle. Fortunately, the game changed as the 20th century drew to a close. Massive initiatives started calculating the exact locations and distances of hundreds of thousands, and later millions, of individual galaxies. The Sloan Digital Sky Survey stands out as a groundbreaking mission. Launching in the early 2000s, this project utilized a specialized telescope at New Mexico's Apache Point Observatory. The survey meticulously logged the coordinates and light signatures of a staggering number of galaxies. By analyzing how their light stretched toward the red end of the spectrum, a phenomenon called cosmological redshift, researchers could accurately calculate each galaxy's distance. Armed with this data, they finally started building genuine, three-dimensional blueprints of the cosmos. Resulting images were absolutely stunning. Instead of a random scatter, galaxies lined up along colossal threads spanning hundreds of millions of light years. These glowing threads met at dense junctions, where immense gravitational forces pulled huge galaxy clusters together. Separating all this action were gigantic, barren gaps. Subsequent projects, like the Dark Energy Survey, pushed these boundaries further out, photographing hundreds of millions of galaxies over massive swaths of the night sky. Thanks to these advanced observations, scientists could trace the universal web with astonishing precision, completely validating the macrostructure Zeldovich envisioned decades prior. It became undeniably clear our universe is woven together like a gigantic, celestial fishing net. Hidden inside this grand net, the cosmic voids stand out as incredibly fascinating areas. These voids are gargantuan pockets of space hosting very few galaxies. You can find examples stretching for hundreds of millions of light years, yet containing nothing more than a tiny smattering of isolated galaxies. Compared to the bustling, star-packed filaments of the web, these voids are practically devoid of matter. Researchers have examined these empty zones carefully to better comprehend the overall distribution of material across the cosmos. A key figure in pinpointing our exact location within this massive framework is Brent Tully, an astronomer famous for studying large-scale galaxy motions. Working alongside his team, Tully identified a gigantic zone of linked galaxy clusters we now call the Laniakea supercluster. Derived from a Hawaiian term translating to heaven, Laniakea is an incredibly appropriate title for such a monumental formation. Our own Milky Way calls this massive gravitational valley home, sharing it with roughly 100,000 other galaxies, all slowly drifting toward a shared gravitational focal point. Still, despite its mind-boggling size, the Laniakea supercluster takes up just a tiny fraction of the broader cosmic neighborhood. Just past its edges, you will find monumental voids where galaxies become incredibly rare. A few of these empty expanses are so huge that a beam of light requires hundreds of millions of years just to cross them. Within these boundaries, material is diffused so sparsely that massive tracts of space are completely devoid of galaxies. When viewed on the grandest possible scale, the universe looks just like a fragile, intricate lace pattern of matter hanging across unfathomable distances. To truly grasp why this layout exists, we must look back at gravity. Gravity is extraordinary precisely because its reach has absolutely no distance limit. Even minuscule clumps of mass can slowly reel in nearby material as eons pass. During the early cosmos, minute density differences started to expand thanks to this exact gravitational pull. Heavier areas steadily hoarded more mass, while lighter areas progressively bled their matter away. Across billions of years, this feedback loop only grew stronger. Material streamed into expanding filaments and clusters, abandoning massive, low-density zones that transformed into cosmic voids. As more mass packed into the filaments, neighboring spaces grew increasingly barren. Through this natural progression, the structural design of the cosmos organically generated colossal arenas of silent, empty space. Consequently, the cosmic web is far more than just a pretty visual phenomenon. It stands as the direct, physical result of gravitational laws operating across unimaginable stretches of time and space. Brilliant galaxy clusters act as the luminous crossroads of this universal grid. Filaments reach out like interstellar highways linking these bustling hubs, while the spaces between them harbor zones where practically nothing exists. These voids easily qualify as the most tranquil neighborhoods in the entire cosmos. Hardly any galaxies call them home, and high-energy events are exceptionally rare. The darkness within these gaps is absolute, broken only by the incredibly dim glow of faraway structures sitting well outside their borders. It is right here, within this monumental framework, that the profound silence of the cosmos truly reveals itself. Our universe is not just empty in a few random, isolated spots. Instead, that vacancy is fundamentally baked into the actual geometric blueprint of cosmic structure. Mass congregates strictly along the threads and junctions, abandoning gigantic zones of pure quiet in between. As a result, the most massive formations in existence naturally carve out the most massive arenas where practically zero activity takes place. It is a deep, universal tranquility permanently etched into the very foundation of the cosmos. But that profound stillness naturally leads to a fascinating puzzle. If the cosmic web was born from minuscule matter variations, what sparked those initial fluctuations? Finding the answer requires rewinding the clock to the absolute dawn of creation. The serene cosmos we observe today was not always peaceful. Journeying back to those primordial epochs, the universe would look completely unrecognizable. Forget the massive voids between galaxies, the soft twinkle of distant suns, or the lazy drift of celestial structures. Instead, you would encounter an environment of extreme, chaotic energy. The infant universe was anything but silent. It was incredibly compact, blisteringly hot, and saturated with radiation. Right after the initial burst of cosmic expansion, everything currently observable was squeezed into a tiny volume at mind-boggling temperatures. Rather than hosting neat galaxies, space was a chaotic soup of basic particles, intense radiation, and superheated plasma. Protons, electrons, and photons were locked in an endless dance, constantly smashing and bouncing in all directions. The universe acted like a roaring, blinding sea of pure power. How did researchers figure this out? The journey starts with a brilliant concept introduced in the early 1900s by Georges Lemaître, a Belgian priest and physicist. Lemaître argued that the cosmos was neither permanent nor unchanging. He theorized that everything blossomed from a vastly tinier, denser condition eons ago. By 1927, he described a continuously stretching cosmos, carrying galaxies apart as space grew. He called this ultra-compressed starting point the primeval atom, a concept evolving into the Big Bang theory. Naturally, this radical idea faced heavy skepticism. Many researchers favored a permanent, unchanging cosmos. Even Albert Einstein originally pushed back against an expanding universe, though he eventually admitted his general relativity equations permitted it. As telescopes improved, proof for an expanding cosmos became undeniable. Stargazers noticed faraway galaxies retreating from Earth, with the most distant ones speeding away the quickest. This trend proved the fabric of space was stretching. If the cosmos is growing larger today, it logically had to be tinier yesterday. Rewinding that expansion, you eventually hit a period when all matter and light were crushed into a sweltering, ultra-dense condition. Pure energy soaked every corner of space, particles smashed together non-stop, and radiation bounced wildly through the thick plasma. The cosmos was essentially a giant, glowing furnace. This fiery epoch left behind an incredible fossil, discovered billions of years later. During the 1960s, radio astronomers Arno Penzias and Robert Wilson used a highly sensitive microwave antenna at Bell Labs in New Jersey. While measuring weak radio emissions, they picked up a stubborn background hiss arriving equally from every angle. Initially figuring their gear was broken, they meticulously inspected the hardware, scrubbed the antenna, and evicted a flock of nesting pigeons. The weird hiss persisted. Finally, they realized this wasn't a glitch. It was a broadcast from the cosmos itself. Penzias and Wilson had discovered the cosmic microwave background radiation, the dim afterglow of the infant universe. This light was released about 380,000 years after the initial expansion, when the cosmos finally chilled enough for protons and electrons to pair up and create neutral hydrogen atoms. Prior to this, photons kept bouncing off unattached electrons in the thick plasma, blocking light from traveling straight. But the moment those first atoms formed, the cosmos turned transparent, letting photons zoom through space unobstructed. Those primordial light particles are still journeying today. Over countless eons, stretching space pulled their wavelengths into the microwave spectrum. This results in an incredibly dim radiation blanket permeating the entire cosmos, standing as the oldest light we can detect. Yet this primordial shine holds incredibly delicate patterns. When researchers examined this background using specialized satellites, namely the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck Observatory, they spotted minuscule temperature shifts across the sky. These tiny variations held massive significance, proving the infant cosmos wasn't perfectly uniform. Certain patches were slightly denser. Those density bumps acted as the first seeds that would eventually sprout into massive galaxies and clusters. Over billions of years, gravity steadily magnified these bumps, dragging matter together into the structures we see today. Consequently, the infant cosmos was rippling not just with matter, but with actual sound. For the first few hundred millennia, the universe was a sweltering soup of photons, protons, and electrons. The outward push of radiation pressure fought the inward pull of gravity, setting up a rhythmic pulsing. Slightly denser patches would cave in under gravity, squeezing the plasma tighter, before radiation forced the area to balloon back out. This tug-of-war generated rhythmic waves rolling through the young cosmos, known as baryon acoustic oscillations. Rippling through superheated plasma instead of air, the physics were strikingly similar to everyday sound waves. Cosmologists like Daniel Eisenstein analyzed these vibrations intensely, as they stamped a permanent mark on galaxy distribution. The gaps between today's massive structures still mirror the layout established by those primordial ripples. The modern cosmos still holds the echo of sound waves from the original plasma. Another incredible interaction was detailed by astrophysicist Rashid Sunyaev. Teaming with Yakov Zeldovich, Sunyaev explored how the cosmic microwave background interacts with massive galaxy clusters. When ancient microwave photons travel through superheated gas inside a cluster, they absorb extra energy by bouncing off highly active electrons. This shifts the overall energy profile of the background radiation, a phenomenon called the Sunyaev-Zeldovich effect. Stargazers rely on this as a potent method for analyzing galaxy clusters and mapping the grand cosmic web. It reminds us the infant universe was a realm of fierce collisions between light and matter, bursting with movement, energy, and sound-like vibrations. As eons rolled on, the cosmos kept expanding. Space stretched wider, pushing physical matter further apart. Particle concentrations steadily dropped, and the fierce collisions that once dominated space started to quiet down. The cosmic furnace gradually lost its heat, the thick plasma dissipated, the radiation diluted, and the universe embarked on its lengthy shift from a loud, hyperactive infancy into the serene, sprawling expanse we observe today. It was a total transformation, driven entirely by the relentless stretching of space itself. Building right on that relentless stretching, we must look at what was quietly happening in the background as the early universe cooled down and matter gradually clumped into the very first stars and galaxies. Space itself was expanding. This concept feels a bit abstract at first because it doesn't act like an ordinary explosion. When something explodes on Earth, fragments are thrown outward through the surrounding air and space. But cosmic expansion is entirely different. Galaxies aren't just zooming through an empty void away from a single central blast point. Instead, the actual space separating these galaxies is stretching out. Every massive region of the cosmos slowly gets bigger over time, naturally carrying galaxies further apart from one another. They aren't soaring through a frozen, static cosmic backdrop. The very fabric of space between them is continuously and gradually growing. This mind-bending idea took shape thanks to several scientists in the early 20th century. A crucial theoretical breakthrough came from the brilliant Russian physicist Alexander Friedmann. In 1922, Friedmann examined Albert Einstein's general relativity equations and uncovered something remarkable. Einstein's math didn't actually demand a stationary universe. In fact, Friedmann proved these equations naturally permitted a cosmos that would either shrink or expand over time. His solutions illustrated how space-time geometry could evolve based on the exact amount of energy and matter present. Back then, this was a wildly radical thought. Most scientists still pictured the universe as a fixed, eternal, and unchanging structure. Even Einstein had initially added a mathematical adjustment to his formulas, known as the cosmological constant, just to maintain a perfectly static universe. However, the actual universe quickly provided evidence to prove Friedmann's expanding solutions right. In the late 1920s, astronomer Edwin Hubble was at the Mount Wilson Observatory, carefully measuring light from distant galaxies. By carefully studying their light spectra, he noticed many galaxies exhibited a shift toward longer, redder wavelengths of light. This phenomenon is called redshift. Whenever light stretches toward the red end of the spectrum, it indicates the object is moving away from the observer. You experience a similar effect with sound when a passing siren changes pitch, famously known as the Doppler effect. Hubble discovered galaxies weren't just moving away from Earth, their speed of recession increased with distance. The farther a galaxy appeared, the faster it seemed to be racing away. This relationship quickly became known as Hubble's law. Simply put, it states that a galaxy's recessional velocity is proportional to its distance from the observer. The more distant the galaxy, the greater the redshift observed in its light. The underlying principle can be expressed in a compact mathematical form, often written in physics, as velocity equals the Hubble constant multiplied by distance. Though the equation is concise, its implications are enormous. If galaxies appear to move away in every direction, the most natural explanation is that space itself is expanding. Just like dots drawn on the surface of an inflating balloon move apart as the rubber stretches, galaxies become more widely separated as the universe grows. This expansion occurs everywhere at once. No single point serves as the center. From any galaxy, all distant galaxies appear to retreat in the same general pattern. Each observer sees a universe gradually stretching outward. Over billions of years, this continuous expansion has had profound consequences for the cosmic structure. Galaxies that once formed relatively close groups slowly drifted farther apart. Clusters of galaxies became much more isolated. The distances between large cosmic structures continue to grow steadily as space itself expands. The universe becomes more spacious, and with greater distance comes greater quiet. When galaxies lie millions of light-years apart, interactions become increasingly rare. Gravitational influence weakens heavily with distance, and collisions occur only occasionally across cosmic timescales. Most galaxies simply travel along their paths through expanding space, drifting quietly and peacefully through the darkness. For many decades, astronomers assumed this expansion would gradually slow down. Gravity, after all, pulls matter together. The combined gravitational attraction of all the galaxies in the universe should act as a cosmic brake, reducing the expansion rate over time. That expectation seemed entirely reasonable, but the universe had another surprise waiting. During the late 1990s, two independent teams of astronomers set out to measure the expansion history using distant stellar explosions known as Type Ia supernovae. These specific supernovae occur when certain white dwarf stars accumulate too much mass and explode with nearly uniform brightness. Because their intrinsic brightness is so well understood, astronomers use them as cosmic distance markers. By comparing how bright they appear from Earth with their actual distance, researchers estimated the expansion rate at different points in history. The teams were led by Saul Perlmutter, Brian Schmidt, and Adam Rees. Their observations ultimately revealed something truly astonishing. The expansion wasn't slowing down, it was speeding up. Galaxies were drifting apart faster and faster, as though some invisible influence were pushing space outward. This accelerating push brought a brand new idea into cosmology: dark energy. Cosmologist Michael Turner made the phrase dark energy famous, using it to label the baffling property of space, or mysterious force, driving this rapid cosmic growth. While normal radiation and regular matter tend to bunch up into physical structures, dark energy does no such thing, appearing instead to be distributed perfectly evenly across the cosmos. Figuring out exactly what it is stands as one of the biggest unsolved mysteries in physics today. Some researchers think it connects back to the cosmological constant that Albert Einstein first proposed. Other experts argue it might stem from fields stretching through spacetime, or perhaps from the inherent energy of the quantum vacuum. Regardless of where it comes from, the result is undeniable. Our universe is expanding at an ever-increasing speed. This rapid speeding up drastically changes the future layout of the cosmos. Because galaxies are rushing away from one another, their chances of interacting have become incredibly rare. Given enough time, the stretching fabric of space will carry countless galaxies completely out of sight, pushing them past each other's observable horizons. Consequently, the grand cosmic scenery is turning into a highly isolated place. Gravity still manages to hold galaxy clusters tightly together, creating little local islands of matter. Yet, outside these gravitational safe havens, the gaps between structures keep widening, making the universe much quieter and emptier. In this way, the stretching of space basically functions as a giant relaxing tool for the cosmos. Think back to the early days of the universe, when particles were crammed tightly together and constantly interacting. Over billions of years, that intense, crowded environment was stretched out into a remarkably roomy setting. During this process, galaxy clusters gathered, individual galaxies took shape, and massive voids of nothingness opened up between them. Since space keeps stretching, these massive gaps are only going to get wider. Ultimately, this means the cosmos is destined to become profoundly silent. Despite the ultimate quietness just mentioned, our expanding cosmos never stops sharing data. Photons constantly bridge massive gaps, delivering messages from remote galaxies, shining stars, and faraway celestial occurrences. Even as the universe grows calmer, it keeps chatting away using a completely different vocabulary than audio. When we think of quietness, we usually picture a total lack of noise. However, outer space isn't genuinely mute, it simply speaks an alternative dialect. Down on our planet, audio moves via tiny squeezes and expansions of air molecules. These physical ripples push adjacent particles along, generating the recognizable vibrations our ears eventually pick up. The vacuum of space, on the other hand, is nearly entirely empty of such particles. Lacking a thick soup of molecules, audio ripples have absolutely nothing to push. Consequently, acoustic vibrations simply cannot journey through the stellar void like they do through water or our atmosphere. Nevertheless, the cosmos continuously beams messages across these barren expanses, and those messages take the shape of illumination. This illumination falls under the wider umbrella of electromagnetic radiation. Contrasting sharply with acoustic waves, electromagnetic energy needs absolutely no physical substance to journey through. Rather, it zips through the void as dancing magnetic and electric fields that constantly regenerate one another as they push forward. This incredible trait enables photons to traverse the empty vacuum while perfectly preserving their data payload. The scientific breakdown of this mechanism emerged in the 19th century, thanks to Scottish researcher James Clerk Maxwell. Previously, experts like Michael Faraday and André-Marie Ampère explored magnetism and electricity as entirely separate subjects. Through rigorous mathematics, Maxwell figured out these two forces are intimately linked. He proved that a shifting electric field births a magnetic one, while a fluctuating magnetic field spawns an electric one. Together, they boost each other in a continuous, self-sustaining loop that shoots through the void. Maxwell calculated these ripples would travel at a very particular velocity, dictated by the magnetic and electrical traits of the vacuum itself. Upon crunching the numbers, his calculated velocity perfectly matched the known speed of illumination. This led to a massive breakthrough. Illumination itself is simply an electromagnetic ripple. This brilliant deduction merged multiple physics disciplines into one cohesive model called classical electromagnetism, while also explaining why photons easily cross the empty void while audio fails. Acoustic waves demand physical stuff. Electromagnetic waves only need fields. After the scientific community embraced Maxwell's concepts, researchers realized visible colors make up just a tiny sliver of a massive electromagnetic spectrum. Various radiation types differ in their frequencies and wavelengths, but they all follow the exact same rules laid out in Maxwell's formulas. Radio waves boast the absolute longest wavelengths, followed sequentially by microwaves and then infrared energy. The visible spectrum sits right around the center, marking the specific, narrow slice our human vision adapted to perceive. Past the visible range, we find ultraviolet rays, X-rays, and ultimately gamma rays, which pack tremendous power into incredibly tiny wavelengths. Every single slice of this spectrum highlights unique cosmic behaviors. Certain celestial events broadcast mostly radio frequencies, whereas others blaze brightest in X-rays or infrared. By analyzing a wide variety of electromagnetic wavelengths, stargazers can assemble a much more detailed understanding of celestial mechanics. Observed through the complete electromagnetic range, the heavens look incredibly lively compared to the peaceful blackness our naked eyes perceive. A major pioneer in launching radio astronomy was an American tinkerer and broadcast hobbyist named Grote Reber. Back in the 1930s, Reber constructed the world's first purpose-built radio antenna right in his Wheaton, Illinois backyard. Using a massive metallic bowl crafted to gather celestial radio frequencies, he started carefully charting the Milky Way's radio output. His data proved our home galaxy broadcasts radio frequencies even in patches where visible illumination seems incredibly dim or totally missing. These initial findings cracked open a brand new observational doorway. As decades passed, radio astronomy grew immensely, empowering researchers to spot cosmic pulses, analyze interstellar gas patches, and observe remote galaxies that would normally stay completely hidden. Today, radio facilities function on a massive scale Reber never could have dreamed of. A truly spectacular example is the Atacama Large Millimeter Array, perched high up in northern Chile's Atacama Desert. This setup features dozens of perfectly coordinated radio dishes scattered over the arid highland. Operating in unison, they act as one colossal instrument able to pick up incredibly weak radio whispers from faraway cosmic formations. Such data exposes chilly gas patches where new suns are igniting, spinning dust rings encircling infant stars, and even the dim residual glow lingering from the universe's absolute beginning. Another game-changing facility is the James Webb Space Telescope. Sent far out past the Moon's orbital path, this incredible machine studies the cosmos chiefly through infrared wavelengths. Infrared illumination is exceptionally handy for examining starbirthing zones and remote galaxies since it easily pierces through the thick dust clouds that block regular visible light. By capturing weak infrared whispers that have journeyed through billions of years of expanding space, this observatory lets researchers peek at galaxies born when the cosmos was just a toddler. Even things that look pitch black to our eyes can shine brilliantly in the infrared range. Throughout the entire electromagnetic range, the cosmos never stops transmitting. Suns radiate illumination generated by atomic fusion deep inside their centers. Entire galaxies beam with the collective brilliance of countless suns. Supermassive black holes spit out intense radiation, while material spirals down into their blazing accretion disks. Dying stars going supernova unleash massive flashes of electromagnetic power visible across mind-boggling distances. Every single one of these messages journeys through the void as electromagnetic ripples. Despite the near-total lack of atmosphere in space, these ripples glide smoothly through the emptiness. Photons departing a remote galaxy might journey for billions of years before finally hitting a lens on Earth. Those photons hold a historical snapshot of the exact environment present at their moment of creation. By examining their brightness, hue, and unique spectral signatures, researchers can figure out the speed, distance, chemical makeup, and heat of the sources that made them. Consequently, illumination acts as the ultimate cosmic courier. Each twinkling dot in the evening heavens is firing a continuous barrage of photons through the void. Every faraway galaxy is silently announcing its existence via electromagnetic energy. These messages surround us completely, yet they never manifest as audio. They show up as illumination. This distinction perfectly explains why the cosmos feels totally mute when we picture it using our biological senses. Human hearing developed to catch atmospheric pressure ripples, not dancing magnetic and electric fields zipping through a stellar vacuum. The heavens might not boom or crash in the conventional way, but they are incredibly active. Rather, the cosmos chats non-stop via electromagnetic patterns that cover mind-bending distances without requiring any physical substance. Utilizing instruments tuned to various wavelengths, researchers have figured out how to eavesdrop on this noiseless dialogue of photons. The cosmos is definitely talking, just without using audio. And whenever those messages expose the most violent occurrences in reality, they prove that underneath the peaceful facade of the heavens, mind-blowing explosions of action are constantly playing out across incomprehensible distances. Even though those incomprehensible distances make the cosmos appear perfectly tranquil to our eyes, that peaceful illusion hides a reality of relentless, extreme action. Out in the deep void, stars are blowing themselves apart, magnetic fields are twisting with galaxy outshining fury, and neutron stars are smashing into one another. So why does the night sky look so serene? It all comes down to the sheer scale of the vacuum. By the time the mind-boggling energy from these cataclysms travels millions or billions of light years, it dissipates into the empty void, leaving our view completely undisturbed. Take the spectacular death of a giant star, for instance. For millions or even billions of years, a star maintains a delicate balancing act. Deep in its core, hydrogen fuses into helium, pushing outward with enough force to hold back the crushing inward weight of gravity. But this nuclear furnace doesn't last forever. Once the fuel runs dry, gravity instantly wins the tug-of-war. The star's inner regions cave in at mind-bending speeds, squeezing matter until atomic nuclei are jammed tightly together. This freefall only stops when the core transforms into a neutron star, an object so unbelievably dense that a single teaspoon of its material would tip the scales at billions of tons here on Earth. This sudden breaking triggers a massive shockwave, blasting the star's outer shell into space in a core-collapse supernova. For a short time, this single exploding star can outshine its entire host galaxy. Yet, because of the vast cosmic gaps, we rarely see them. In fact, the closest one visible without a telescope in modern history was supernova 1987A, which erupted in the Large Magellanic Cloud, a small neighboring galaxy. Even that relatively nearby blast took 160,000 years for its light to reach our eyes, proving that the universe operates on a scale where even the loudest explosions are muffled by distance. But supernovae aren't even the most energetic shows in town. That title belongs to gamma-ray bursts, which are fleeting, ultra-intense flashes of radiation. In just a handful of seconds, these bursts can pump out more energy than our sun will generate over its entire multi-billion-year lifespan. Astronomers were completely baffled by them for decades. We only discovered them in the 1960s when satellites built to monitor secret nuclear weapons tests on Earth picked up unexpected flashes of gamma radiation coming from deep space. Instead of human activity, the sensors were blindsided by the cosmos. It took years of intense observation and theoretical work to figure out what was going on. Astrophysicist Stan Woosley played a massive role in solving this mystery by helping to build theoretical models for these events. His research demonstrated that certain gamma-ray bursts happen when a truly colossal star collapses directly into a black hole. As the star falls inward, it creates a rapidly spinning disk of material around the newborn black hole. From the poles of this spinning system, jets of high-energy particles are fired outward at nearly the speed of light. When those jets punch through the star's outer layers and hit the vacuum of space, they generate incredibly focused beams of gamma radiation. Because these beams are so tightly concentrated, we can only see a gamma-ray burst if the jet happens to be aimed directly at our planet. When that alignment occurs, the burst briefly becomes the most luminous phenomenon in the observable universe before quickly fading into darkness. Then we have the spectacular crashes of neutron stars. Remember, these are the ultra-dense leftovers of massive stars, packing more mass than our Sun into a sphere no bigger than a typical city. Their gravitational pull is staggering. When two of these stellar corpses are locked in a binary orbit, they slowly spiral toward each other. As they dance closer, they bleed energy by emitting gravitational waves, the subtle ripples in the very fabric of spacetime that Albert Einstein predicted with his general theory of relativity. Their orbital motion speeds up until they finally smash together in a catastrophic merger, unleashing a massive tsunami of both gravitational waves and electromagnetic radiation. This spectacular crash is also a cosmic forge, creating heavy elements like platinum and gold through a mechanism called rapid neutron capture. For a long time, gravitational waves were just a mathematical prediction. However, the early 21st century saw the completion of machines sensitive enough to feel these microscopic spacetime distortions. The most famous of these is the Laser Interferometer Gravitational Wave Observatory, universally known by its acronym, LIGO. Developed over decades by brilliant minds including Rainer Weiss, Kip Thorne, and Ronald Drever, this massive US-based facility uses lasers to measure unbelievably tiny shifts in distance caused by passing waves. LIGO made absolute history in 2015 by catching the very first confirmed gravitational waves, which were generated by two black holes merging over 1 billion light-years away. Even though the signal lasted just a fraction of a second, it proved that massive, energetic collisions were echoing through the deep cosmos. A few years after that milestone, another detection captured the spacetime ripples from a neutron star collision. This was a game-changer because, for the very first time, astronomers could observe both the gravitational waves and the electromagnetic radiation from the exact same event. Telescopes all over the globe immediately pivoted to look at that patch of sky, watching the collision's aftermath bloom into a glowing, expanding cloud of stellar debris. Yet another flavor of cosmic extreme comes from magnetars. These are a very uncommon breed of neutron star equipped with magnetic fields so ridiculously strong that they can actually warp the physical structure of atoms near the surface. Theoretical work by astrophysicists Robert Duncan and Christopher Thompson helped explain how these intense magnetic fields are generated. Their models suggest that a fast-spinning neutron star can amplify its magnetism through a dynamo-like process, creating fields trillions of times more powerful than Earth's magnetic field. Occasionally, the magnetic field lines inside a magnetar will suddenly shift or fracture, triggering what astronomers call a starquake. This fracture unleashes a colossal flare of high-energy radiation. In just a brief moment, a single magnetar flare can blast out as much energy as our Sun produces over hundreds of thousands of years. But once again, the sheer scale of the universe swallows this violence whole. A magnetar erupting in a faraway galaxy will send its radiation traveling for millions of years. By the time that faint whisper of light finally washes over Earth, the actual explosion is ancient history. This exact pattern plays out everywhere you look. Black holes consume matter and fire massive radiation jets across intergalactic space, magnetars erupt, neutron stars crash, and stars detonate. Every single one of these events unleashes mind-boggling power, but they are separated by such colossal gulfs of empty space that they almost never interact. The universe looks incredibly peaceful from our vantage point, not because it lacks action, but because all that action is buffered by unimaginable distances. The sheer volume of empty space dilutes the violence, keeping the cosmos dark and quiet. But this profound silence naturally leads to a fascinating follow-up thought. If natural astrophysical events can send light and radiation across the universe, couldn't intelligent beings do the exact same thing? Despite listening to the skies for decades, we haven't heard a single peep from alien civilizations. For most of our history, the night sky seemed quiet simply because space is big. But in the 20th century, scientists started doing the math. With hundreds of billions of galaxies, each holding hundreds of billions of stars, it seems statistically inevitable that some of those worlds would spawn technological societies capable of building technology and broadcasting their presence. So why the radio silence? This exact puzzle was famously summed up by physicist Enrico Fermi with a simple question: where is everybody? Fermi reportedly brought this up during a casual lunchtime conversation at Los Alamos National Laboratory in the early 1950s. While his colleagues were chatting about the potential for extraterrestrial travel and advanced civilizations spreading across the galaxy, Fermi pointed out a glaring contradiction. If intelligent life is common in the Milky Way, some civilizations would have had millions of years to expand, explore, or communicate. Even traveling at modest speeds, a civilization capable of interstellar travel should theoretically have spread throughout the galaxy over cosmic timescales. Yet, we see no obvious spacecraft, no unmistakable signals, and no clear signs of vast technological structures surrounding distant stars. This mismatch between the high probability of habitable worlds and the total lack of detected civilizations became known as the Fermi question, or the Fermi paradox. To tackle this problem systematically, astronomer Frank Drake introduced the Drake equation in 1961 at a scientific meeting focused on the search for extraterrestrial intelligence. Instead of trying to guess a single, precise number, Drake created a mathematical framework to think about the many factors involved. His equation considers several crucial ingredients: the rate at which stars form in a galaxy, the fraction of those stars with planetary systems, the number of planets that might support life, the fraction where life actually arises, the fraction of life-bearing worlds where intelligent species evolve, the fraction that develop technology capable of sending detectable signals, and finally, the length of time those civilizations continue transmitting. When multiplied together, these variables estimate how many technological civilizations might exist in a galaxy at any given time. While the equation doesn't provide a definitive answer because many variables remain uncertain, it highlights an important idea. The silence of the cosmos might not mean intelligent life is rare. It may simply reflect the extreme difficulty of detecting civilizations across immense distances. Still, if they are out there, why haven't they called? One popular answer is the Great Filter, a concept developed by economist and philosopher Robin Hanson. This theory suggests there is an extremely difficult barrier somewhere along the long chain of steps required for intelligent life to develop. This filter could occur early, making the origin of life itself incredibly rare, or it could occur later, preventing civilizations from surviving long enough to spread across the galaxy. If such a filter exists, it perfectly explains why the universe appears so quiet. Another intriguing solution is the zoo hypothesis, proposed by scientist John Ball. He suggested that advanced civilizations might deliberately avoid contacting developing worlds like Earth, treating our planet like a protected wildlife preserve or a cosmic zoo. In this scenario, advanced beings observe emerging societies without interfering, perhaps even hiding their presence to avoid disrupting our natural evolution. While purely speculative, it highlights how little we know about the behavior, priorities, and communication methods of hypothetical extraterrestrial cultures. Meanwhile, scientists on Earth continue the hunt. One of the most prominent organizations is the SETI Institute, which stands for the Search for Extraterrestrial Intelligence. Researchers use massive radio telescopes to scan the sky for unusual patterns, looking for narrow-frequency transmissions that repeat in structured, artificial ways. Yet, despite decades of observation, no confirmed technological signal has been detected. The sky remains quiet, which may simply reflect the enormous challenge of searching across the vast electromagnetic spectrum and the immense distances separating stars. Physicist Ronald Bracewell explored another angle through the concept of interstellar communication networks. He suggested that advanced civilizations might deploy automated probes or communication relays across the galaxy to act as silent messengers. These devices could wait quietly for the right conditions to communicate with emerging civilizations, but detecting them would be extraordinarily difficult. The fundamental problem is that the distances between stars stretch across trillions upon trillions of kilometers. Even signals traveling at the speed of light require years, decades, or centuries to cross these gaps, making communication a slow, delicate process resembling conversations stretched across vast eras rather than moments. Because of this, civilizations may simply miss each other. One society might transmit signals for a few thousand years and fade away, while another arises millions of years later in a distant region. Their signals would never overlap. In a universe billions of years old, the lifetimes of technological societies may be brief flashes. If those flashes rarely occur at the same time and in the same region, the sky will naturally remain quiet. Ultimately, the silence might not mean emptiness. It might simply mean separation across the vast structure of the cosmos. Signals travel slowly, distances remain immense, and civilizations appear and disappear across millions of years. From Earth's perspective, the night sky still seems silent, yet beneath that silence lies a deeper question about how information travels across the universe, driving astronomers to keep searching for signals of all kinds, from both intelligent life and the natural processes of the cosmos itself. Building on that quest to decode the cosmos, the breakthrough in capturing extraterrestrial radio waves happened entirely by chance, long before dedicated instruments existed. Back in the early 1930s, American engineer Carl Jansky was employed by Bell Telephone Laboratories. He wasn't stargazing. His actual job was tracking down static, disrupting transatlantic radio broadcasts. To tackle this, he engineered a massive, rotating antenna to pick up weak transmissions from all directions. This bizarre contraption resembled a giant carousel constructed from wire and metal tubing. As he reviewed the data, Jansky spotted an anomaly. Amidst the usual static, a specific interference pattern repeated with clockwork consistency. Its intensity peaked and dropped exactly once every 23 hours and 56 minutes. Because this timeframe aligns with Earth's rotation relative to the distant stars rather than our Sun, the transmission was clearly extraterrestrial. Digging deeper, Jansky pinpointed the origin to the constellation Sagittarius, aiming straight at the thick core of our Milky Way. This breakthrough represented the very first time humanity detected radio waves from outer space. By surprise, Jansky unlocked a brand new way to observe the cosmos, proving the heavens are actually buzzing with radio frequency energy. Unseen transmissions perpetually wash over us, delivering details about highly energetic events far past our solar system. Even with such a monumental find, radio astronomy didn't instantly explode into a mainstream science. Instead, its early progress relied heavily on the passion of one dedicated hobbyist. Grote Reber, an amateur radio enthusiast, was completely captivated by Jansky's findings. Eager to explore these enigmatic cosmic broadcasts, Reber constructed a personal radio telescope. During the late 1930s, he erected a massive parabolic dish right in his Wheaton, Illinois backyard. Spanning about 30 feet in diameter, his creation gathered celestial radio waves and funneled them into a central receiver. Nightly, Reber aimed his homemade dish at various sky patches, meticulously logging every signal. Over several years, he produced the very first comprehensive radio maps of our galaxy. His efforts proved radio broadcasts are scattered throughout the Milky Way, showing that areas packed with dust, gas, and high-energy particles generate radio waves even without visible light. Thanks to his relentless commitment, radio astronomy evolved from a quirky side project into a legitimate branch of science. Over following decades, technological leaps led to sharper radio telescopes, allowing researchers to uncover bizarre new phenomena. A truly spectacular breakthrough happened at the University of Cambridge in the late 1960s. Jocelyn Bell Burnell, a graduate student, was sifting through data from a radio array built to examine faraway sources. Reviewing the charts, she spotted a weird sequence of repeating blips arriving with mind-boggling consistency. The rhythm was so perfect it felt manufactured. Some scientists playfully dubbed the source "Little Green Men," wondering if they found an alien beacon. However, additional study pointed to a completely natural source, the pulsar. These are incredibly dense, fast-spinning neutron stars left behind after massive supernova blasts. They feature powerful magnetic fields shooting concentrated beams of electromagnetic energy from their poles. As the star whirls around, these beams slice through the cosmos much like a lighthouse beacon. Whenever a sweeping beam points toward Earth, our telescopes register a quick burst of radio energy. While some twirl multiple times a second, others spin slower, yet every single one keeps time so perfectly they compete with atomic clocks. This find, attributed to Bell Burnell and advisor Anthony Hewish, exposed a hidden layer of galactic action, proving optically invisible objects flash rhythmic radio codes across the Milky Way. As the field matured, experts realized a multitude of extreme cosmic events generate powerful radio emissions. Faraway galaxies harboring supermassive black holes shoot out gigantic jets of high-energy particles stretching far outside their borders. These streams blast intense radio waves as charged particles corkscrew through magnetic fields at nearly light speed. Furthermore, areas actively birthing new stars produce detectable frequencies. Vast clouds of chilly hydrogen gas give off subtle radio signatures at specific wavelengths. By charting these, researchers track gas movement inside the Milky Way, exposing an active cosmos brimming with events optical telescopes miss. However, catching these faint whispers demands incredibly delicate equipment. By the time radio waves travel from remote galaxies to Earth, their strength is incomprehensibly weak. To snag them, scientists construct massive arrays of antennas that gather energy over huge swaths of land, merging inputs to mimic one gigantic telescope. Currently, a highly exciting endeavor is the Square Kilometer Array. This project will deploy thousands of individual dishes across isolated landscapes in South Africa and Australia. Once finished, this network will function as one unified facility, boasting a combined collection area of nearly 1 square kilometer. Such sensitivity will empower scientists to pick up broadcasts from the furthest cosmos, studying the very first structures emerging after the Big Bang. Additionally, this mega-observatory will hunt for subtle signatures from cosmic hydrogen, chart the grand architecture of the universe, and explore extreme zones encircling supermassive black holes. Using such incredible tools, researchers are essentially eavesdropping on the cosmos, swapping biological ears for electronic receivers. Rather than capturing physical sound waves moving through an atmosphere, these dishes record electromagnetic field vibrations journeying across the void. Scientists translate this information into visual maps, usable data, and occasionally, actual audio frequencies we can hear. In this way, the field turns unseen cosmic chatter into an experience that feels just like listening. Though space doesn't create acoustic sound conventionally, it never stops transmitting radio broadcasts exposing its secret behaviors. Neutron stars flash their rhythmic beats, active galaxies spew massive jets, cold hydrogen clouds shimmer in radio bands, and ancient structures transmit faint energetic echoes across billions of light-years. Thanks to radio telescopes, we understand the seemingly peaceful night sky is actually packed with subtle electromagnetic messages. And hidden among all this cosmic chatter is a crucial hint regarding the very dawn of creation. It takes the form of a subtle, omnipresent glow permeating the entire cosmos, acting as a leftover echo from an era when everything was vastly younger and infinitely more violent than the universe we see today. Building on that violent past, we must look beyond supernovas, faraway galaxies, and puzzling radio bursts to find another pervasive signal. This particular emission is incredibly delicate, remarkably old, and completely ubiquitous. Scientists refer to this phenomenon as the cosmic microwave background radiation, which is widely considered the most ancient illumination still visible to us. Rather than originating from any specific celestial body, this energy saturates the vacuum of space with near-perfect consistency, reaching our telescopes from every angle. To researchers, this omnipresent glow is a spectacular treasure, a direct fossil from the very first instant the cosmos became transparent. Grasping the origin of this background energy requires picturing the cosmos in the immediate aftermath of the Big Bang. During those initial phases, everything was astonishingly compact and blisteringly hot. Physical matter and radiant energy blended into a luminous soup, forcing protons, electrons, and light particles into a chaotic dance of continuous collisions. Because of this endless bumping, illumination was trapped. Any given light particle would instantly smash into a charged particle, bouncing off in an unpredictable trajectory. Consequently, the entire cosmos was entirely impenetrable to light, functioning much like the inside of a remarkably thick cloud. However, the continuous stretching of space brought a steady temperature drop. Approximately 380,000 years following the initial explosion, the environment chilled sufficiently to allow protons and electrons to bond, creating neutral hydrogen. Scientists call this milestone recombination, even though it technically marked the very first occasion these subatomic pieces ever joined. With electrons now locked into atoms, they stopped deflecting wandering light particles. Illumination was suddenly unshackled, permitted to stream unimpeded across the void. The exact energy unleashed during that precise epoch has been cruising through the void ever since. As eons passed, the ongoing inflation of space pulled the wavelengths of this primeval illumination, slowly pushing it down into the microwave band of the electromagnetic spectrum. An initially ferocious burst of energy slowly faded into a delicate hum that only highly calibrated equipment can detect. Despite its diminished state, this subtle emission stands as a cornerstone of modern astrophysics. Radio astronomers Arno Penzias and Robert Wilson first stumbled upon this background energy in the 1960s. Operating a massive radio receiver in New Jersey, the duo kept picking up a stubborn microwave hiss radiating from all points in the sky simultaneously. Initially blaming faulty hardware, they thoroughly checked their gear, scrubbed the dish, and even evicted pigeons roosting inside the machinery. Nevertheless, the mysterious hum persisted. Ultimately, the pair understood they were dealing with the delicate residual warmth of the infant cosmos, not technical static. This breakthrough offered massive support for the Big Bang theory, which had previously predicted exactly this kind of ancient echo. Recognizing the magnitude of this finding, researchers immediately started engineering new ways to examine the phenomenon closely. Various orbital projects were sent up to chart this microwave backdrop with escalating accuracy. Among the pioneers was the Cosmic Background Explorer, frequently referred to as COBE. Sent into orbit during the late 1980s, this satellite gauged the thermal profile of the background energy spanning the heavens. Its findings verified that this emission maintains a nearly flawless thermal consistency throughout the viewable cosmos, hovering just a few degrees above absolute zero. Such incredible evenness proved that the infant universe was remarkably smooth when viewed from a macro perspective. However, the true triumph of the COBE project was finding minuscule deviations hidden inside that smooth blanket. The orbiter spotted microscopic thermal shifts, registering discrepancies of merely a few millionths of a degree. Far from being instrumental glitches, these microscopic bumps were genuine physical traits of the primordial universe. George Smoot, a prominent cosmologist instrumental in analyzing the satellite's numbers, memorably dubbed these microscopic shifts the seeds of cosmic architecture. These slight deviations highlighted pockets where physical material was just a bit denser than surrounding areas. Across countless millennia, gravitational forces magnified these marginal contrasts. The slightly denser zones pulled in even more mass, slowly giving birth to the galaxies, galactic clusters, and the grand cosmic web we observe today. Essentially, the colossal formations populating our current sky are the direct descendants of barely perceptible wrinkles in the primordial microwave glow. Subsequent projects built directly on Kobe's work. The Wilkinson Microwave Anisotropy Probe, or WMAP, lifted off in the early 2000s to generate a vastly superior chart of the microwave backdrop. This observatory exposed the architecture of those thermal ripples with improved clarity. By examining delicate designs hidden in the background energy, WMAP allowed experts to sharpen calculations regarding the age, shape, and makeup of the cosmos. Through this data, researchers pinned down the universe's age at roughly 13.8 billion years. Furthermore, the project delivered compelling proof that regular material constitutes just a tiny sliver of reality, while dark energy and dark matter rule the cosmic stage. Following this, the European Space Agency's Planck satellite pushed boundaries even further. Debuted in the early 2010s, this observatory scanned the microwave backdrop with unprecedented precision. The resulting charts displayed highly complex ripple designs spanning the heavens, delivering the sharpest portrait ever captured of the infant universe. These specific designs lock away vital clues regarding the physical environment immediately following the Big Bang. Through meticulous examination, researchers can piece together the early developmental stages of the universe, uncovering exactly how material was spread out and how initial formations started to take shape. Viewed through this lens, the microwave backdrop functions much like a baby picture, not capturing individual stars or galaxies, but snapping a portrait of the cosmos itself during its infancy. The illumination we capture right now started its epic voyage when space was merely a few hundred millennia old, vastly predating the ignition of the first stellar bodies. Across countless eons, this light has navigated the stretching void, serving as a messenger bearing the historical ledger of the primordial era. Whichever way we point our telescopes, we are greeted by this exact same archaic radiance. Though the cosmos might seem completely vacant and hushed, it remains saturated with this delicate reverberation of its own birth. While incredibly delicate, this emission narrates a remarkably deep tale. It proves that even the most desolate, silent patches of the void hold onto the fingerprints of occurrences from eons past. Space is absolutely brimming with data, safely stored within energy waves still traversing vast distances. Therefore, the profound quiet of space does not mean history is missing. Rather, it is a peaceful blanket draped over an ancient archive. As the cosmos keeps aging, deeper physical mechanisms will dictate its destiny, slowly morphing the chaotic, fiery environment of antiquity into an increasingly vast and serene domain. Building on that shift toward serenity, we have to realize that the universe's profound silence isn't just about massive distances. It is fundamentally about the passage of time. Over countless billions of years, the cosmos has been steadily transitioning in a specific direction, guided by a principle physicists call entropy. This fascinating concept first came to light in the 1800s when researchers started diving into the mechanics of heat, energy, and physical systems. A major pioneer in this field was the Austrian physicist Ludwig Boltzmann. He wanted to figure out why certain physical actions only ever happen in one direction. For instance, heat always moves from a warm object to a cold one, gas always expands to fill its container, and energy naturally evens out as time passes. These common, everyday occurrences paved the way for the second law of thermodynamics. Simply put, this law declares that the overall entropy of any closed system will always go up. You can think of entropy as a gauge of disorder, or more accurately, a way to count how many tiny, microscopic setups are possible for a specific physical condition. Naturally, systems drift toward setups that can happen in countless different ways, rather than staying in highly organized states that need exact, specific conditions to survive. Boltzmann captured this brilliant idea in a neat formula that links entropy directly to the number of tiny configurations a system can have. To sum it up, Entropy is equal to Boltzmann's constant multiplied by the natural logarithm of all the possible microscopic states. Even though this mathematical rule was first created to explain steam engines and lab gases, its reach goes way beyond industrial machinery. These exact same thermodynamic rules govern stars, entire galaxies, and the whole universe. Cosmic structures are completely bound by thermodynamics, and stars are the perfect illustration. A star is born when gravity crushes a massive cloud of gas, mostly hydrogen, inward. As this cloud shrinks, gravitational energy turns into intense heat, spiking the temperature right at the center of the newborn star. Eventually, it gets hot enough to ignite nuclear fusion. Deep inside the stellar core, hydrogen atoms smash together to create helium. This fusion reaction unleashes a staggering amount of energy, which slowly pushes its way to the surface and finally bursts out as radiation. Starlight then journeys across the void, transporting energy away from the blazing, dense core and out into the freezing emptiness of space. From a thermodynamic viewpoint, this entire cycle boosts entropy. The energy starts off tightly packed inside the star's center, but as time goes on, it scatters outward in every direction as radiation. Because of this, stars basically function as giant cosmic engines that steadily scatter energy throughout the universe. However, even these mighty engines eventually run out of steam. Stars burn through their nuclear fuel over millions or even billions of years. Once that fuel starts running low, the delicate internal tug-of-war between gravity and radiation pressure shifts. Some stars balloon outward into red giants, while others crush inward to become ultra-dense remnants like white dwarfs, neutron stars, or black holes. No matter the specific path, the ultimate outcome is identical. Energy scatters further, heat pushes outward, and entropy climbs higher. When we look at cosmic timescales, this slow leaking of energy is exactly what cools down and calms the universe. During the early days of cosmic history, matter was jammed tightly together, and particles were constantly bumping into each other. But as space expanded and temperatures dropped, matter organized into galaxies and clusters, while light shot outward across ever-growing stretches of the void. The cosmos simply became roomier and much more thermodynamically chilled out. The brilliant physicist Roger Penrose has dug deeply into these concepts while analyzing the thermodynamics of the universe. Penrose highlighted a fascinating paradox. The early universe, even though it was incredibly hot and dense, actually had very low gravitational entropy. Back then, matter was spread out incredibly smoothly, lacking any major large-scale structures. In the world of thermodynamics, this extreme smoothness was actually a highly organized, low-entropy state. As time marched on, gravity started magnifying tiny bumps and irregularities in how matter was distributed. Slightly thicker patches pulled in even more stuff, ultimately giving birth to stars, galaxies, and massive clusters. By building these intricate gravitational systems that are great at shuffling energy around, these structures drove up the universe's total entropy. Black holes are the ultimate heavy hitters in this process. Thanks to the groundbreaking theoretical physics of Jacob Bekenstein and Stephen Hawking, we now know that black holes hold mind-boggling amounts of entropy. Their event horizons act like massive hard drives, storing unimaginable amounts of information about all the matter and energy that has tumbled inside. In reality, black holes are likely the highest entropy objects in existence. As stars die and galaxies age, an increasing amount of matter gets permanently trapped inside these dark giants. Over mind-bendingly long periods, black holes completely take over the thermodynamic profile of the cosmos. But amazingly, not even black holes are immortal. Thanks to weird quantum quirks right at their event horizons, they slowly leak energy in a phenomenon called Hawking radiation. Over stretches of time so vast they defy human comprehension, black holes will literally evaporate away. Because of this, the universe just keeps marching toward a state where energy is spread out as evenly as possible. Hot spots cool down, dense clumps break apart, and radiation wanders across endlessly expanding stretches of space. Entropy just keeps climbing. This unstoppable trend perfectly explains why the universe looks so peaceful on a grand scale. As energy diffuses and matter drifts further apart, systems interact less and less. Sure, explosive events like supernovae or neutron star smash-ups still happen, but they are just rare, isolated flashes rather than a constant, chaotic roar. The cosmic neighborhood gets quieter, not because everything completely stops, but because the energy is diluted across such ridiculously huge volumes of space. The exact same thermodynamic rules that make a hot cup of tea cool down in a chilly room are the ones sculpting the evolution of stars and galaxies over billions of years. Energy diffuses, strict order surrenders to more likely, messy arrangements, and the cosmos slowly inches toward perfect thermodynamic balance. When you look at it this way, the silence of the cosmos isn't some spooky mystery. It is simply the unavoidable result of physical laws. The second law of thermodynamics acts as a silent director for the universe's evolution, pushing energy to scatter and guiding systems toward a state of perfect equilibrium. Looking ahead into the deep future, this exact process will keep molding the destiny of everything. Stars will ultimately burn out completely. Galaxies will fade into darkness. Space will keep stretching, pushing cosmic structures further apart than we can possibly imagine. The intensely violent, energetic birth of the universe will gracefully transition into a profoundly tranquil cosmic landscape. It will be a reality where energy is smeared incredibly thin across infinite distances, making absolute quietness the default state of existence. And as researchers continue to probe the ultimate fate of the cosmos, they are working hard to map out exactly how this incredibly slow thermodynamic voyage will play out across timeframes that truly boggle the mind. Building on that mind-boggling timeline, the silence we notice in space right now isn't just a fleeting phase of our current epoch. Modern astrophysics tells us it's actually a single chapter in a massive, ongoing saga stretching across unfathomable durations. The universe is steadily drifting toward an even more peaceful state. Right now, stars act as the main powerhouses driving all visible action. By fusing hydrogen into helium, they unleash colossal bursts of radiant energy. This brilliant mechanism lights up entire galaxies, fuels planetary ecosystems, and forges the essential building blocks for life itself. However, this stellar engine runs on a strictly limited fuel supply. The primary ingredient is hydrogen gas drifting through gigantic interstellar clouds. As eons pass, gravity pulls chunks of this gas together into tight pockets, sparking the birth of fresh stars. Every wave of star creation eats away at this universal fuel tank, meaning the reserves are steadily shrinking. To figure out what happens when this countdown extends way past the universe's current age, astrophysicists have dug deep into cosmic aging. Two scientists who really spearheaded this research are Fred Adams and Gregory Laughlin. They zeroed in on the extreme far future of cosmic evolution. By looking at how long stars live, how they form, and how gravity dances between them, Adams and Laughlin mapped out the ultimate destiny of galaxies over staggering timescales. Their findings reveal that our current boom of star birth is just a temporary blip in the grand timeline. Eventually, galaxies will completely exhaust the raw ingredients required to forge new suns. Giant hydrogen clouds will either get entirely used up or blasted out of their host galaxies by violent events like supernova explosions and galactic winds. Without enough gas left, the creation of new stars will hit the brakes hard, and the cosmos will slowly start to dim. In fact, this shift is already well underway. Astronomers see that the cosmic star-making rate actually hit its peak billions of years ago and has been declining ever since. While galaxies are still minting new stars today, the overall speed is just a fraction of what it used to be. Fast forward far enough, and star birth will become incredibly rare. Existing stars will keep shining for a remarkably long time, particularly the tiny ones. Red dwarfs, which pack much less mass than our sun, sip their nuclear fuel with incredible efficiency. A few of these little powerhouses could stay glowing for trillions of years, but even these ultra-enduring stars will meet their end. Once they burn through their last drops of hydrogen, they will cool down and fade out, turning into superdense cores called white dwarfs. Given enough eons, these leftover cores will keep losing heat until they freeze into ultra-cold spheres known as black dwarfs. When this happens, Galaxies will be packed with dead stellar husks instead of brilliant suns, plunging the cosmic scenery into deep shadow. Meanwhile, a completely different class of objects will take the reins: black holes. Supermassive black holes already sit at the hearts of most major galaxies, our Milky Way included. Packing the mass of millions or billions of suns, they wield colossal gravitational muscle. As stars burn out, these dark giants will likely become the undisputed rulers of the cosmos. Random gravitational tugs will sometimes kick objects completely out of their home galaxies, leaving behind a sparse crowd. Complex orbital dances will also cause many leftover stars to spiral straight down into the central black hole. Over immense stretches of time, these black holes will gorge themselves on this matter. But even this feeding frenzy has an expiration date. Thanks to a quantum quirk predicted by physicist Stephen Hawking, black holes leak energy through Hawking radiation. This bizarre effect makes them slowly evaporate. While a standard stellar mass black hole will take far longer than the universe's current age to evaporate, the supermassive ones will require time spans so ridiculously huge they defy comprehension. Yet, in the very end, even they will vanish. Adding to this future silence is the relentless stretching of space. Because cosmic expansion is accelerating, galaxies will be pushed further apart as the clock ticks. Areas of space we can see today will eventually get swept past the edge of our observable universe. Galaxies will end up as lonely islands stranded in a constantly expanding sea of nothingness. Way down the line, anyone looking up from inside a galaxy won't be able to spot the broader universe outside their local neighborhood. Faraway galaxies will retreat so fast that their light will simply never make it to us. From that vantage point, the cosmos would feel incredibly small and hushed. The night sky would be stripped of distant galaxies, and cosmic structures would be profoundly cut off. These forecasts sketch out a cosmos that just keeps getting more tranquil. The fiery, energetic youth of the universe will smoothly transition into a mellow twilight ruled by dying stars and freezing remnants. Finally, even those remnants will wink out, leaving a reality where action is practically non-existent and energy is smeared thinly across unimaginable distances. This grand trajectory perfectly mirrors the thermodynamic rules we talked about earlier. Energy dissipates, structures change, and the universe inches closer to a state where things rarely interact. In that remote tomorrow, the silence of space won't just be an illusion caused by vast distances. It will be the very core identity of the cosmos. Yet hidden inside this silent tomorrow is a truly profound thought. The universe isn't just a giant machine blindly following the laws of thermodynamics. It is also the very stage where conscious minds like ours woke up, learned to read its ancient history, and started pondering its ultimate fate. Realizing we happen to exist during a surprisingly lively window of cosmic time really makes you stop and think. Our current universe, glowing with bright stars and swirling galaxies, might just be a short, sparkling prologue to a much longer, vastly quieter epic. And wrapping our heads around that epic naturally sparks some incredible questions about exactly where humanity fits into such a colossal, gently aging cosmos. When we ponder our place in this colossal, gently aging cosmos, it naturally leads us to look up. Even though the universe feels incredibly hushed, humanity has never simply looked away. Over the centuries, our curiosity has expanded right alongside our growing awareness of just how massive and intricate the cosmos truly is. What started as a sky full of myths and philosophical musings slowly transformed into a target for rigorous science. We didn't just learn to gaze at the stars, we figured out how to measure them. This journey kicked off with basic tools, but eventually blossomed into a worldwide mission featuring giant telescopes and advanced observatories. These machines let us probe a seemingly peaceful universe, pulling hidden messages right out of the silence. Essentially, the sheer stillness of space has become our ultimate scientific laboratory. Leading this charge, the European Southern Observatory stands out as one of the most daring partnerships in modern astronomy. Established in the 20th century, this group runs several massive observatories perched high in the deserts of northern Chile. They didn't pick this spot by chance. The Atacama Desert boasts some of the clearest skies on Earth. Up there, The air is incredibly dry, the atmosphere is steady, and being far from major cities means almost zero light pollution. Thanks to these perfect conditions, telescopes can pick up incredibly weak signals from faraway stars. Scattered across this rugged landscape are gigantic instruments built to catch tiny flickers of light that have journeyed across the cosmos. Perhaps the most famous setup run by the European Southern Observatory is the Very Large Telescope. This is a network of powerful instruments working in perfect harmony on a mountain peak called Cerro Paranal. These machines scan the heavens with mind-blowing sensitivity, giving astronomers the power to investigate planets circling distant suns, track the movement of entire galaxies, and peer into the extreme environments swirling around supermassive black holes. It turns out that even the faintest whispers of starlight can lead to monumental breakthroughs. The profound quietness of space is exactly what makes these measurements possible. Since there is practically no matter floating between the stars, electromagnetic signals can cruise across mind-boggling distances without getting scattered or soaked up. By the time that ancient light finally hits a telescope, it is packed with detailed information about whatever created it. Every single photon acts as a tiny cosmic messenger. Translating these messages takes more than just fancy hardware. It requires brilliant scientists who meticulously crunch the data. Over the years, their hard work has turned delicate patterns of starlight into mind-blowing insights regarding the fabric of the universe. Astronomer Vera Rubin, for example, completely revolutionized modern cosmology. Rubin spent a huge chunk of her career investigating how galaxies spin. Using spectroscopic data gathered from observatories across the United States, she closely tracked how stars orbit the cores of spiral galaxies. Based on classical physics and visible matter alone, stars sitting further out from the galactic center should move much slower than the ones near the middle, just like outer planets orbit the sun slower than inner ones. However, Rubin's data showed something totally wild. The stars way out on the edges were zooming around just as fast as the stars hugging the center. The outer edges of these galaxies were spinning way too fast for visible matter to explain. This massive discrepancy provided rock-solid proof for dark matter, a mysterious, invisible substance that pulls on things with gravity but refuses to emit or bounce back any detectable light. Thanks to Rubin's precise measurements, dark matter is now a foundational pillar of modern cosmology, proving how much a subtle observation can flip our scientific worldview upside down. The deep calm of the universe is what allows these discoveries to happen. Because cosmic signals cross gigantic voids without constant interference, astronomers can pick up unbelievably faint shifts in light, radio waves, and other radiation. Minuscule changes in wavelength tell us how galaxies are moving. Gentle ripples in background radiation map out the structure of the infant universe. Tiny dips in brightness expose alien worlds orbiting faraway stars. Every breakthrough depends on catching signals that would totally vanish in a louder environment. The silence of space is a massive perk. If the cosmos were packed with endless collisions, thick matter, and chaotic turbulence, the signals astronomers depend on would be completely drowned out. Instead, the colossal emptiness separating stars lets information glide across the void with stunning clarity. The universe might seem totally mute, but its messages arrive perfectly intact. Catching these pristine messages requires jaw-dropping engineering precision. Telescopes need to stay perfectly steady while tracking objects that crawl across the night sky. The detectors inside them must be chilled to unbelievably low temperatures, so their own heat doesn't create thermal noise that drowns out weak cosmic whispers. Even the physical placement of these observatories is heavily scrutinized. Whether it is a remote mountain peak, a desert plateau, or a satellite floating far above Earth's atmosphere, every location is picked to eliminate interference. In these ultra-quiet zones, astronomers capture signals that have been traveling for billions of years. A single photon shot out by a distant galaxy might finally hit a detector after an unfathomably long trip, instantly becoming a vital puzzle piece in humanity's quest to understand the cosmos. This undertaking highlights something spectacular about our species on a tiny rock circling an average star. Despite living in a vast, quiet universe mostly indifferent to our daily lives, we have figured out how to catch and decode signals from the deepest reaches of space. The machines we build on mountains and shoot into orbit are currently gathering data on events that played out billions of years before our planet even existed. Through patient watching and exact measurements, astronomers are constantly translating the hidden codes carried by light and radio waves through the silent void. That cosmic calm, which people used to mistake for pure emptiness, is actually our greatest window for discovery. It ensures the faintest signals survive their epic journeys, giving observers on our little world a chance to study the grand universe wrapping around us. Ultimately, these observations spark a much deeper realization. The silence of the cosmos isn't just a random physical trait. It is the perfect, peaceful backdrop that allowed conscious beings to evolve, look up, and start asking massive questions about reality and our place within it. And naturally, those big questions guide us right into the deeper meaning of what it is like to exist in a universe that is both unfathomably huge and beautifully quiet. When we step back and view things from the scale of our everyday human experience, that profound cosmic silence can actually catch us completely off guard. Our home planet is rarely ever truly silent. Wind rustles through trees, waves crash onto shores, and animals constantly interact with their surroundings. Even the atmosphere buzzes with kinetic energy. Noise and movement are simply normal features of life on our little world. But zoom out to the broader cosmos, and the rules change completely. The sheer volume of space is so massive that even the most explosive celestial events end up incredibly far apart from one another. Galaxies drift through giant voids of nothingness, and stellar interactions take millions or even billions of years to play out. Viewed this way, the peaceful cosmos suddenly makes sense. This silence does not mean the universe is sitting still. Rather, it reflects the unbelievable distances involved. Gravity directs this serene dance, pulling material together to build stars, galaxies, and massive clusters. Yet, gravity is also incredibly patient. It rarely causes abrupt or chaotic movements across vast distances, gently coaxing matter into highly organized, long-lasting arrangements instead. For instance, a gas cloud softly compresses over millions of years before igniting into a star. Meanwhile, galaxies spin in elegant arcs around their centers, and huge galaxy clusters slowly glide together, pulled by their shared gravitational weight. These movements pack incredible power, yet they happen at a glacial pace. Consequently, the universe's grand architecture is built from countless slow-motion gravitational pulls stretching across eons. Rather than messy chaos, the cosmos settles into reliable routines lasting billions of years. Galactic disks spin precisely, planets follow predictable orbits, and giant clusters trace steady paths along the cosmic web. This peaceful vibe is really just ultimate stability, not a lack of action. Fundamental physics pushes matter to build persistent structures, and once built, these systems stay remarkably calm. Think of this cosmic hush as a perfect equilibrium. Energy still flows through stars and swirls through galaxies, but the vastness of space dilutes that action, making everything look serene from afar. Some brilliant minds see deep philosophical meaning in this tranquility. The renowned physicist Freeman Dyson, for example, pondered the distant future of the cosmos and where intelligent life fits in. Dyson proposed that consciousness could creatively adjust to the changing universe, even as stars fade and galaxies grow quieter. He highlighted that the cosmos offers thinking beings a unique mix of challenges and opportunities. While the void of space might feel intimidating at first, that exact stillness allows fragile signals to journey across the cosmos undisturbed. Honestly, this profound quiet makes astronomical discovery possible. If space were packed with endless collisions and constant noise, the weak signals astronomers hunt for would vanish instantly. But because space is so calm, light travels for billions of years while keeping its message intact. Every photon hitting a telescope brings information from the exact time and place it originated. A faint signal arriving today could reveal a galaxy formed eons ago or a distant star exploding long before Earth existed. These messages travel in total silence, yet they contain extraordinary stories. Cosmic silence practically invites curiosity. The night sky looks peaceful, but careful observation reveals hidden layers of intense action on enormous scales. Behind that calm facade, stars are born and die, neutron stars collide, galaxies grow, and the universe slowly expands. All this continues while the sky appears completely relaxed. This contrast between a peaceful appearance and underlying activity has captivated scientists and philosophers alike. It reminds us that human senses provide a limited view of reality. What seems silent may buzz with hidden signals, and what looks empty may contain structure and energy. The universe quietly invites investigation. Freeman Dyson suggested that scientific exploration is partly about learning to listen more carefully to nature. Using observatories, detectors, and telescopes, we push our senses far beyond their natural limits. Through them, astronomers detect faint radiation, gravitational waves, and subtle patterns in the cosmic microwave background. Each discovery reveals another layer of the universe hidden within the calm night sky. The stillness of the cosmos becomes a source of wonder rather than emptiness. It provides conditions for light to travel, signals to survive, and knowledge to accumulate across generations. In a turbulent universe, such delicate information might never reach us. Instead, the immense quietness of space allows a small world orbiting an ordinary star to receive messages from billions of years of cosmic history. Seen in this light, the calmness of the universe becomes something beautiful. It reflects the deep order emerging from fundamental physical laws. Gravity shapes galaxies, thermodynamics guides energy flow, and cosmic expansion stretches space itself. Together, these processes produce a universe that evolves slowly, steadily, and quietly across unimaginable time scales. Within that vast calm, stars shine, galaxies rotate, and light travels patiently across the depths of space. And on one small planet, observers look upward and begin to understand the story written in that quiet sky. As we gaze up from our small world, deciphering the tale etched into the tranquil heavens, we come full circle. The profound quiet we perceive flows directly from the fundamental architecture of reality. What we once mistook for a void is actually the result of immense scale, physics, and time. The cosmos isn't hushed due to a lack of activity. Rather, the mind-boggling gaps between events prevent their energies from mingling. Tranquility is simply the native language of an incomprehensibly massive cosmos, holding an epic tale spanning from the Big Bang to the remote destiny of space itself. Typically, when we picture the cosmos, our minds jump to explosive drama. We envision supernovas detonating, galaxies crashing, and titanic forces molding space. While these violent phenomena absolutely happen, stepping outside and looking up with bare eyes tells a different story. The dominant feeling is absolute serenity. Pinpoints of light rest peacefully against a pitch-black canvas, making the scene feel entirely frozen. To figure out why the heavens seem so peaceful, we must examine a few core characteristics of the universe. The most significant reason boils down to the mind-bending immensity of space. The gaps separating stars, galaxies, and massive clusters are almost impossible to fathom. Take Proxima Centauri, the closest star to our Sun. It sits over 4 light-years away, meaning the photons hitting our eyes tonight started their trip more than 4 years ago. When you stretch interactions across such colossal gaps, they become incredibly uncommon. Stars almost never collide. Entire galaxies might only glide through one another once every few billion years. Furthermore, even the most violent cosmic detonations happen so far apart that their shockwaves never mix. Distance effectively waters down the energy, translating directly into silence. The second major piece of the puzzle comes down to how sound and matter behave. For acoustic waves to move, they absolutely need a physical medium like solid rock, liquid water, or air. Here on Earth, noise travels because molecules vibrate and bump into their neighbors. Out in the interstellar void, however, matter is incredibly scarce. Across huge swaths of our galaxy, you might only find a few atoms in a single cubic centimeter. Without a thick substance to carry vibrations, acoustic waves simply cannot journey across the stars. Consequently, blasts that would shatter eardrums on our planet happen in total, eerie silence in the vacuum of space. But a lack of noise certainly doesn't mean the cosmos is sitting still. Rather than using acoustics, the universe chats using electromagnetic radiation. Energy formats like infrared heat, radio frequencies, and visible light zip through the void without needing any physical material. Back in the 19th century, James Clerk Maxwell proved that fluctuating magnetic and electric fields can ripple through a total vacuum. Stars broadcast visible light generated by nuclear fusion. Entire galaxies beam out radio frequencies as charged particles zip through magnetic fields. Meanwhile, black holes spit out intense radiation as material gets sucked into their swirling accretion disks. The cosmos is buzzing with constant transmissions. They just show up as light instead of audible noise. To catch these invisible messages, humanity has built incredible astronomical observatories. Massive ground-based facilities like the Square Kilometre Array, the Atacama Large Millimeter/Submillimeter Array, and the European Southern Observatory are engineered to snag weak electromagnetic signals from the deep cosmos. We've even launched hardware into orbit. The James Webb Space Telescope captures ancient infrared light from galaxies formed billions of years ago. Before it, missions like the Planck satellite, the Wilkinson Microwave Anisotropy Probe, and the Cosmic Background Explorer meticulously charted the cosmic microwave background left over from the dawn of time. Every facility functions as a highly tuned radio dial, locked onto a specific slice of the electromagnetic spectrum. These captured messages prove the void is teeming with action. When giant stars die, supernova detonations unleash staggering power. When dead neutron stars smash together, they create ripples in spacetime, which the Laser Interferometer Gravitational Wave Observatory successfully detects, a triumph pioneered by Kip Thorne and Rainer Weiss. Additionally, highly magnetic neutron stars known as magnetars blast out extreme radiation flares, driven by the intense magnetic dynamics theorized by Christopher Thompson and Robert Duncan. Even the faint whisper of the cosmic microwave background holds vital clues about the exact conditions present when the cosmos was a mere few 100,000 years old. Phenomena that would look apocalyptic up close become incredibly subtle when viewed across billions of light years. The ongoing expansion of space piles even more tranquility onto this scene. When Edwin Hubble first proved the universe was expanding, he showed that galaxies are constantly drifting away as space stretches. Later, researchers Adam Rees, Brian Schmidt, and Saul Perlmutter discovered that this stretching is actually speeding up, driven by dark energy. As these galactic islands drift further apart, the chances of them interacting drop significantly. As the cosmos inflates, all the action inside it gets progressively more isolated. The laws of thermodynamics push this calming trend even further. Ludwig Boltzmann's foundational work showed that physical systems naturally drift toward higher entropy, a state where energy spreads out. Stars burn through their nuclear fuel, converting it into light that radiates endlessly. Eventually, even black holes will slowly boil away via Hawking radiation. This slow, steady dilution of energy naturally results in a much more peaceful cosmic neighborhood where physical interactions are incredibly rare. When you step back, the profound hush of the cosmos makes perfect logical sense. Colossal gaps minimize collisions. The near-perfect vacuum blocks acoustic waves. Electromagnetic ripples carry the mail instead of pressure waves. The relentless stretching of space pushes galaxies apart, and thermodynamics slowly diffuses energy across the grand expanse. Combined, these elements forge a reality that feels incredibly serene. What initially feels dead and silent suddenly bursts with hidden life the moment you apply the right scientific equipment. Researchers have learned how to eavesdrop on the faintest whispers traveling across the void. Every particle of light caught by a lens holds a secret. Every radio burst explains a faraway star. Every spacetime ripple tells the epic tale of giant objects crashing together far outside our Milky Way. To truly grasp this silence, We have to remember that human biology evolved to survive on a tiny rock, not to naturally perceive events stretched across billions of light years. But once we build machines to boost our senses, that quiet canopy transforms into a symphony of data. Ultimately, the serene facade of the night sky is just a reflection of its staggering size. Grasping this concept perfectly sets the stage for our final thoughts, shifting our focus from the mere physics of a quiet cosmos to the profound meaning of conscious life existing within such a massive, peacefully unfolding reality. Building on that profound realization, we can finally look up at the night sky with a new perspective. When you gaze at the stars on a clear evening, the heavens seem incredibly peaceful. Distant suns twinkle steadily against a dark, seemingly vacant backdrop, giving the illusion that nothing is moving or changing. However, this tranquil surface masks a dynamic reality. Throughout the cosmos, stellar nurseries birth new suns while older ones meet explosive ends. Massive gravitational frameworks guide drifting galaxies. Meanwhile, black holes consume material and blast energetic jets across the void, and smashing neutron stars create violent ripples through space-time. The cosmos isn't hushed due to a lack of action. It seems that way because all this intense activity is stretched across mind-boggling distances. This immense scale alters our perception. When phenomena are spaced apart by millions or billions of light years, their energy dissipates over colossal volumes. An explosion that would shatter eardrums up close transforms into a barely noticeable flicker by the time it reaches a faraway viewer. Furthermore, the physical void plays a crucial part. Because the interstellar vacuum lacks almost all matter, acoustic waves cannot propagate like they do through Earth's atmosphere. Rather than relying on sound waves, the cosmos broadcasts using electromagnetic radiation. Light acts as the ultimate messenger. Every photon hitting a telescope delivers a dispatch from a distant corner of reality. Many of these luminous postcards embarked on their journeys eons ago, patiently crossing an expanding void before arriving at our planet. By decoding these transmissions, scientists have pieced together the history of existence. The cosmic microwave background provides a baby picture of reality from when it was just a few 100,000 years old. Radio arrays pick up the rapid spinning of pulsars in our Milky Way, and orbital observatories capture galaxies that took shape during the dawn of time. Every breakthrough proves the serene nighttime canopy conceals staggering complexity. The actual architecture of the cosmos also enforces this tranquil vibe. Gravity clumps material into galactic clusters, leaving gigantic, nearly vacant voids, while cosmic expansion continually pushes these clumps further apart. Consequently, intense action is heavily buffered by immense gaps. This inherent hush flows directly from fundamental physics. Thermodynamics diffuses energy outward to reach balance, while gravity locks material into enduring formations. Combined, these mechanisms forge a reality that transitions at a relaxed pace. Yet this serene environment offers an incredible advantage. Thanks to the vast, hushed nature of space, fragile transmissions can cross unfathomable gulfs without getting scrambled. Photons from remote galaxies endure multi-billion-year treks, and tiny variations in background radiation safely carry data from the dawn of time. If the cosmos were noisy, this precious data would be lost. Because of this, studying the stars is essentially an exercise in listening. Our observatories push human perception past its biological limits to capture and decode the universe's whispers. Through dedicated observation, we have transformed a seemingly mute canopy into a library of cosmic tales. We now hear narratives of suns igniting inside freezing gas nebulae, of galactic evolution, and of the early universe lingering in faint radiation. Ultimately, this tranquility isn't about emptiness, it is purely a matter of scale. The sheer size of the cosmos makes the most ferocious phenomena look gentle from afar. While standing under the stars might make you feel isolated in a mute void, the truth is far more beautiful. Reality is endlessly chatting with us, sending luminous words across billions of years. And right here, on a tiny rock circling an average sun, observers have figured out how to tune in. The heavens are never truly mute, they are simply waiting to be understood.